information. People actually, the machine learning community meets once in a while and conducts what is like the Olympics of algorithms. So, I mean, they don't actually compete in on a problem set, but they bring in a large number of people and who are practitioners of machine learning, respected practitioners of machine learning, and ask them what their favorite algorithms are. And then do a counting of that, polling, voting and all that, and arrive at some ranking. They had one in 2000 and the latest one happened in 2006. And this was published in 2007. So this is not too old. This passed 9 years back. And the top 10 algorithms in data mining are these. Number one is C4.5, then K-means, SVM, a priori, expectation maximization, PageRank, AdaBoost, KNN, Nailbase, and CART. Now, interestingly, you don't find linear logistic regression here because this is a community of machine learning. I am sure any statistician in the team would have rated the linear logistic regression, So that's an interesting thing. C4.5 and CART. 1 and 10 are rule-based models, and a priori is a rule-based model. We are going to learn, so actually if you think about it, so far what did we do? Just naive-based, right? In this list? In this list we only learned naive. Did we do KNN? Not systematically, I mean I have mentioned probably KNN, but I don't think it's part of your syllabus. There's more to KNN than what we did. So systematically we only did naive-based. So the course, we have 4 classes left, right? In the next 4 classes, we are going to do C4.5, K-means, a priori, expectation maximization, AdaBoost, and CART. SVM, I don't think is part of this curriculum. You will be, so quite a bit of machine learning is packed for the last 4 days, right? Most of the things that we did are statistics so far, statistical learning. So by the end of this course, you will learn 1, 2, 3, 4, 5, 6, 7 of the 10 algorithms. If you, PageRank is what made Google what, at least many people believe that this is fundamental to entire Google's strength. But it's so specific, but for Google, you wouldn't have found it here. Because it's just applied in search and a little bit of graph-based problems, but the others have a lot of rich history behind them, right? So, so what we are going to look at now, at least of these, C4.5, CART, a priori, and AdaBoost. 4 of the top 10 are rule-based.
Sir, out of all those things, PageRank is a true data mining algorithm, but rest of them are machine learning algorithms, right? So, is there a difference between?
Is there any difference between machine learning and data mining? First question. So, no. To the best of my knowledge, in 1980s, when people were working on small sets of data, so Quinlan, when he invented C4.5, his paper says, I have experimented this on a large data set of 500 records. Right? So they used to call it machine learning in those days. Now 1990s, management schools adopted that. Okay, the machine learning because of its interest. And they started running it on larger data sets of 50,000, 100,000 records. So their community started calling it data mining. Predictive analytics. Data mining became more popular than machine learning. In 2000, when Facebook and Google started adapting it on millions and millions of records, they started calling it data science. So fundamentally, there's no difference in the algorithm. So only there are 2 schools, statistical and, statistical and machine learning are 2 approaches. Decision trees, neural nets, genetic algorithms, all these are the machine learning approaches. Regression, Nailbase, Bayesian belief nets, all these are statisticians' approaches.
Just to confirm, there is no element of prediction in PageRank, right? It's just a data mining.
Well, it depends on how you define the prediction. If the prediction is about future, no. If the prediction is about how ugly this this website is, yes, there is. So there is a computation. It's a very elegant algorithm. Actually, they use Markov chains to arrive at it. It's not relevant to what we are doing, so we will not be covering that. Right. So next 3 days, based on our schedule, 2.5 days based on how much time really it will take, we are going to spend on rules. Okay? Generating rule injection is going to be the focus, which is very different from what we have been doing so far. Actually, I like rules a lot, simply because they are easy to understand, even more easier than the output of a linear regression. Linear regression gives an equation, y is equal to a1 m1 x1 plus m2 x2 plus m3. It's easy because you know if m1 is positive, you know m1 is directly proportional, y is directly proportional to x1. If m1 is negative, you know y is inversely proportional to x1, indirectly, I mean negatively proportional to x1. And based on the quantity of m1, you know whether x1 is more important or x2 is more important, and we have done weights, and so there's a lot of understanding that you gain from an equation. That's what makes it very exciting. But rules have directly 2 advantages. The first one is a rule by nature is non-linear. What a rule is, if x1 and x2, then x3, or then y. If x1 and x2, then y. Or more formally, if x1 is between a and b, and y1 is between c and d, then, sorry, x2 is between c and d, then y. Right, so that's what is a rule. It's called, it's the most fundamental type of rule, and it's called propositional rule. So the advantage is, if this is x1, this is x2, if x1 is between a and b, and x2 is between c and d, then y. x1 is between a and b. A, x2 is between c and d. C, d. So a rule is a rectangle in 2 dimensions, a cuboid in 3 dimensions, a hypercuboid in n dimensions. Right? So by nature, this is nonlinear. In logistic regression, you have a line separating things. In linear regression, you have a line or a plane going through the data. But in a rule, you actually have a rectangle. So you can think of a logistic regression as separating the data into a smaller number of buckets. One, if it's a binary, you have just one bucket on one side, other bucket on other side. In a decision tree or a any rule-based system, you can have multiple rectangles. And one rectangle is good customer rectangle, another rectangle closes the bad customers, then good customers, then bad customers. So I can divide the data into a lot more number of things. And hence, many a times this is more accurate. So the first advantage is this is typically more accurate than a classic regression. The second advantage is it's probably more explainable. Which one do you think is more explicable? Equation or a rule? Rule, right? Yeah, I also think so. So though some people do not want it, rule is definitely more explainable if there are few of them. If I have 100,000 rules, then probably a single equation is better. If x1 is between a and b and x2 is between c and d, then y1, x2 is like that. If I have a rule that is very, very long, if x1, x2, x3, x4, x5, x6, x7, x8, x9, then y, yeah, right. You know, so if a rule is short and there are few of them, they're definitely much more insightful, right? And that's the reason why I like decision trees. They are more accurate and more easier to understand. And what is more exciting is they are almost as fast as a logistic regression to build. As easy, as fast as easy as logistic regression. See, if I give you data, ask you to build logistic regression, what skill do you need? And honestly, nothing. You just need to know that code, LM, binomial or whatever. That's it. The algorithm takes care of everything. What coefficients to put, whether to put positive or negative, dummy, creating dummies also is automatically built. Similarly, in a decision tree, you don't have to take any decision. You just ask the system to build a decision tree, and it does. Whereas in a more advanced model like regularization, I need to define my lambda, I need to define my alpha, I need to look at other parameters, neural network. I need to decide how many layers I have to put in each layer, how many nodes I have to put, and what is the learning coefficient, what is the inertia. I need to define and experiment on a variety of parameters. So the quality of a network that I build will be different from the quality of a network that is going to be built by someone who has been in that domain. Expertise counts in support vector machine, in gradient boosting machines, in neural net, deep learning. Expertise counts. Whereas logistic regression and decision tree, you run a model, Quinlan runs a model, the answer is the same. And that is very, very useful if you think about it from a scalability perspective.
So the other regression, linear, there are certain underlying assumptions, right? Normality,
Here I don't have technically, non-parametric model, right? So that's another big advantage. And there are some, we'll see what are the additional advantages, but that's the reason why machine learning community as a group loves rules and rule detection.
So based on a little bit of exposure to decision tree, I found that even two different people can have different trees given the underlying data because they could choose various other parameters, right? So
Like?
There's a cost parameter.
You can choose. You can play with it a bit more, but you are right. If you cost is one of those interesting things, I'll talk about that. But you don't have to. You given a data, you run a decision tree. As long as the training data is same, you are most likely to get the same decision. Right. So what I want to do in the next few sessions is, first I want to actually analyze the rule, goodness of a rule. We have seen goodness of a model. We studied precision, recall and all that stuff, and mean square error and all that stuff. But rules have to be dealt very differently, because rule doesn't talk about the entire data. A given rule talks about only a subset of the data. What is a rule at some level? If x, y, then z. It's a filter. If you think of an Excel, I'm just applying a filter. If x is equal to k, y is equal to l, then z. So I am just going to that column, applying a filter, and the next column, applying a filter, and then I have a subset of the data. So rules talk about only a subset, and hence all these precisions and recalls don't make any sense. We need to arrive at newer metrics. So we spend time on understanding the goodness of the rule first. And then I will talk about 3 different techniques to generate rules. Okay? Today probably we'll look at 1 or 2, and then next class we will do 1 more. And then we'll talk about some very exciting developments where rules become more accurate and less explicable. We'll talk about that. Right? That's the overall plan. So let's now start with the goodness of it. So this is a rule. If x and y and z, then a. Now I will never use these terms, but for whatever they are worth, let's learn it. This is how you see them in literature. X, Y, and Z are called antecedents, and A is called consequent. Left hand side, right hand side, essentially. This one, let's keep it, it will be useful. Number of antecedents. Length of a rule is number of antecedents. So it's an informal definition. I use it. I don't think it's a textbook thing. Okay, and in rules I'm going to talk about many things that are not part of a textbook. Okay, because for the past 3 years, I've been doing a lot of work on generating rules. And one of the questions that I always have is, if you get excited and start generating rules, you will generate 1,000 rules from the data. So I built a product called Intusio. And one of the things that does is, if a decision tree can generate 100 rules, I generate 1,000 or 2,000 rules. And the average and median quality of my rules are better than what a decision tree can do. Okay, so I went and posted that, and then the company and filed some 4 patents on that. So the company says, okay, good, you have generated 2,000 rules, can you prioritize and author them? 2,000 rules to go through step by step, no business user has time. So tell me the 10 that I should get. And I'm going to talk about some statistical metrics, some really cool statistical metrics. But as I found very quickly, that's inadequate. Statistically, now I pick 500, and organizing them statistically didn't really make sense many times. Okay. So I needed to define a lot more metrics on my own to identify and make the best guess of which rules are more exciting. Okay, I'll talk about all of them. So some of them are textbook, some of them are my own thoughts. You can extend them, drop them, feel free, whatever you want to do. Okay, but they may not be as popular. Okay, given that, 3 most common statistical metrics of a rule are support, confidence, and lift. In fact, whenever someone specifies a rule, they specify what is its support, what is its confidence, what is its lift. Okay. Let's understand what those 3 terms are. I've taken our bank data set and I constructed a simple rule. If CC average is medium, then loan is equal to accept. If CC average is medium, then loan is equal to accept. Right? Totally, there are some 13 data points. 3, 3, 6, 3, 9, 3, 12 plus 1, 13 data points. How many data points is this rule supporting? So for how many data points, the left-hand side and the right-hand side, if CC average is medium, then loan is accept. Left and right are 3. So the support of the rule is 3 over 13. Support of the rule is the number of records in the data, and that frequentist kind of an analysis, that is the probability that the rule is right. Probability of the rule. Support is the probability of the rule, right? Joint probability, P of A and B, where A is the left hand side, B is the right hand side. P of A and B is the support, right? What do you think is a good rule? A rule with large support or a small support? Small support.
Because support, you don't have as many decisions to make. Mostly you are making the same decisions over the data.
You mean decision?
For example, if this had support of 100%, that means that rule does not have any purpose. Not solve. But then
Why doesn't it solve any purpose? I mean, it doesn't, you're right, it doesn't solve any purpose. This is actually something that hit me when I went to a business. It solves a purpose, but most likely your customer knows it. If I come back and tell, hey, all men are mortal, I looked at 100 million records and then all of them died in the past. So a rule with a support of 100 million, all men are mortal. Philosophically it's a very revealing thing, but everyone knows it, right? So if I I'm currently working with a company called Vunik, like women's fashion thing. If I go back and tell them, majority of your customers are women between 20 and 60, they say, yeah, right. Why did I pay you for this, man? They sell women's fashion goods, right? So I don't even have to double check that the rule is known to everyone. That's why what I noticed is the moment a rule has more than 50% support, I start getting less and less excited about that rule. It may be very true, but the business uses it. All people who, there's a 90% probability that those who took decoction will also take milk. Yeah, right. So that those are the kind of things. On the other hand, a very small rule maybe is fluke, statistically irrelevant. So people who are wearing red shirt and traveling by Honda car and arriving at 11:45 to the office from the back door are brilliant programmers, let's say. And in the entire 2,000 Genders Associates, probably 2 people followed that. Only 2 people had all those conditions met. Right? So that's a rule of 2 out of 2,000. Will I believe that, or it is just that on that day, by fluke, they did that? Most likely it's by fluke. So, too small a rule is statistically not reliable. Too large a rule is probably known to everyone, known to the business user. So, your hunt should be somewhere in between. For me, the rules that I really like most are those rules that are between 5 to 10% support on larger data sets. I mean, once I have 1,000 plus records, 5 to 10% support rules are really exciting. 1 to 5% are okay, but we haven't yet figured out the problem of how to know what is the least number of records. I did something pretty cool, I'll share with you. But think about it. How do I know when do I start believing that it is not fluke? What is the minimum number? A rule of thumb by statisticians is 30 records. Right? I mean, statistically you have more than 30 start. But if I totally have only 100 records, 30 is a huge number.
Depends on the
Maybe I think like 10 to 15% of the data should be covered.
That is a huge rule. If I Amazon, which has probably 2 million transactions a day, if it's building a rule with 10%, that is like 300,000 people have to obey. For them, even 1% rules are good enough. If I have 2 million transactions, 1% is 20,000, which is not bad at all. 20,000 people can't be fluke, right? So maybe even 0.1 is reliable. So so finding minimum support is a non-trivial task. And many a times we believe the domain expert knows, but they don't have a clue. One of the things that people say is ask the business user. And what will you go and ask the business user, when will you start believing my rule? No, they don't know. Right? So we have to figure out a statistical way to do it.
So in addition to it, is the Y variable always fixed? Because if the Y variable is fixed, then the addition of the support for all the decisions should add up to 100%, right? Or can there be different Y variables for each of the decisions?
No, it's like linear regression. Same Y variables.
Like the example.
So the support of all the rules put together should add up to 1. So they explain how many.
So in the thing which you created, the decision are supposed to create 100 rules, then you create suppose 1,000 rules.
Good. How did I do that?
So by default the support goes down when you create rules.
Not because of that. It's a very good question. Decision tree essentially creates only one non-overlapping rule structure. I used multiple methods to create several overlapping rule structures. So one rule describes the data from here to here, another rule describes the data from here to here. So then you have many more
And
possibilities.
support goes over 100%.
Was higher, around the same. We haven't yet figured out a single metric that does that. All this is going to be homework for you. And I'm going to just give you a lot of complicated stuff as homeworks in this. Wherever I got stuck, I'm going to ask you to solve it for me. Okay? Good. We know what support is. Support is joint probability. Support is essentially what fraction of records obey left hand and right hand. And high support customer knows probably is too trivial. High support makes a rule a trivial rule. And low support makes a rule a fluke rule. So somewhere in between I have to get. Okay. Now, if CC average is medium, then loan is accept. How many times when the left hand side is true, the right hand side is also true? If I tell you a rule, if CC average is medium, then loan is accept. What I want to know is, what is the probability of B given A? Right? What is it here? There are 3 times when left hand side is right and the right hand side is right all 3 times. So there is a 100% probability. If you tell me the left hand side, I am 100% confident that the right hand side will happen. If on the other hand the rule is, if CC average is low, then loan is not accept. Now there is 1, 2, 3, 4, 5, 6, 7, 8 times the left hand side is right. Of them only 6 times the right hand side is right. What is P of B given A for the rule? If CC average is low, then loan is accept. Loan is not accept. Loan is 0. 6 by 8. 6 by 8. 3 by 4. 75%. That is called the confidence of the rule. Confidence of a rule is how many times the right hand side is right given the left hand. P of B given A, which is equal to P of A intersection B divided by P of A. Probability of A intersection B is equal to probability of B given A times P of A, right? If I take P of A, in probabilistic terms, confidence is conditional probability by marginal probability, right? If I want to complicate it like that. I am saying support is P of A intersection B, confidence is P of B given A. But you also know P of A intersection B is equal to P of A times P of B given A. So confidence is equal to support divided by P of A. If you want to look at it from probability, in its simplistic terms, the confidence of a rule tells me how confident I should be about the rule. Essentially, if the left hand side is right, how confidently I say the right hand side is right. So in a very business terms. Support tells me how much data is supported by this rule. Confidence tells me how much of confidence I have in the rule itself. Now, aren't they sufficient to define a rule? A good support and a good, now, is there any, just for support we had some dilemma. Low support is fluke, high support is great, high support is trivial, middle support is the best. In confidence, do you see any conflict like that? Do you want a low, do you think a low confidence is better, high confidence is better, medium confidence is better? High, right? Yeah, it's a linear function. You want the higher the confidence, the better the. Okay. Oh. I don't know why she gets activated. Right. Do you think a decent support and decent confidence is good enough to define the goodness of a rule? No. High confidence, yeah, decent support and high. Let me step back. Do you think support and confidence are good enough metrics, sufficient metrics to define how good a rule is? Let's look at it. So you gave me a project. We took up a project on from Subway on what are the topics of how profiling their customers. So I stood right at the order counter and I'm looking at customers. And I'm looking at various attributes, and the final attribute is whether they came to buy or they didn't come to buy. Okay. So I kept looking at one of the attributes. So finally, I came up with a rule that says if the gender is male and they are wearing a shirt, they buy. Right? Now this rule has approximately 50% confidence, support. Because 50% of the customers are men and 50% are women, 50% support, and 100% confidence. If given that they are male and they are wearing a shirt, they are buying a something. So is that a useful rule? Why not? 50% support, 100% confidence. On the left hand side is right hand side is right anyway.
This is complemented by another rule which also talks about people, men who are not wearing shirt and instead wearing
Yeah.
something else. Then it would be a
But so I need some other metric. Because support and confidence don't tell me anything about the other rule. Right? So these are called, these are called an obvious class rule. I am standing at the cash counter of a Subway, so there is no one who comes there to not buy. Right? So if I have 100 records and all 100 are buys, I could have as well said, if nothing, then they buy. That itself is a decent rule, 100% confidence. If nothing, they buy. So if the right hand side is biased, 99% or 100% is only a single class, then the rule is as good as not, no rule is an empty rule, null rule has a 100% confidence. So we,
in this case it means we are not creating decision trees for brand metrics.
by the way, we are not yet creating any decision trees, we are only creating rules.
Yeah, so we are not creating rules for that metric. Maybe the interest could be some other metric.
Metric as a,
So for example, if everyone in the data set buys a sum, then the business question could never be who buys the sum and who doesn't buy the sum.
I agree. So in a very trivial way, in the extreme case, yes, you are not interested in that. But I took this example of 100% and 0% just to show you the importance of the third metric. Okay. But even if there are fraud kind of situations, there's a 95% data in one side and 5% data in the other side. So when I'm forming a rule on the non-fraud situation, I will get low metric. This metric will be hurt. Any rule that I build on the other side of fraud will be very good on this metric. So I need to be able to quantify that.
Coming to the fraud situation, this frauds generally have low occurrence, right?
Yeah.
So by default, fraud cases will have very less support in any case.
Exactly. So what is the minimum support is a bigger question there. So your 30 and 40 are 10% or 5%. We haven't figured that out yet. Yes. By the way, I just want to clarify what at this point we are doing is metric of a rule, goodness metric of a rule. Rule can be generated by decision trees, by prism rules, by a priori rules, association rules. I personally use genetic algorithms. So rules can be generated by multiple mechanisms. Rule induction is a branch of machine learning in which there are multiple techniques. Please do realize that decision tree is only one of the and definitely the most popular rule induction technique. But there are many other techniques and we are going to study all of them. So when you see a rule, you could have induced it using any of the techniques. And for any of the techniques, it is independent. The metrics that we are learning are suitable the moment you see a propositional rule. This is called a propositional rule. First order propositional rule actually. This is the least complicated rule. If x and y, then z. There are some rules which have second order, which has an inference built in. All men are mortal. Jesus Christ was a man. And hence Jesus Christ is a mortal, was a mortal. Now there is a second order rule. Right? I have a base statement, I have an inference, you could induce, there are techniques to induce second order rules. But again, the problem with second order rule is the beauty is charm is lost. People, the moment the rule gets higher order, expectability is lowered and lowered. So the first order if then rules are the most beautiful for a business user. So majority of the work focuses on generating first order rules. Okay. So this is confidence.
What is a good threshold for confidence? About what confidence?
We'll talk about that. Good. We'll talk about that. So, is there a threshold for a confidence? Okay. We'll look at that. What is the threshold? Minimum support and minimum confidence are two things that we have not yet studied. Right? Luckily, the third one lift is a much more easy to define that way. If I reverse the rule, if loan is accept, then CC average is medium. What is the support and confidence? So I switch the left hand side and right hand side. Loan is accept, then CC average is medium. What is the support? Support is same. Confidence? Now there are the 6 cases when left hand side is right. 6 or 7? 7 cases when left hand side is right. Only 3 of them right hand side is right. Right? So 3 by 7. Which is different. So when if I switch a rule, support should not change because it's joint property. A intersection B intersection A. Confidence is conditional property. A given B given A. They better be different. Likely that they are different. Right? So confidence switch changes if the rule is switched. Okay. Another small problem. A transaction table contains 100 records. We want to find rules with support greater than 20% and confidence higher than 80%. That is the target. X is the left hand side, Y is the right hand side. X is present in 25 transactions, Y is an obvious class, which means Y is present in all 100. Then, if X then Y, what is the support? If X then Y. So this is what I want to find. If X then Y, support. How many times X and Y are together present? 25. So 0.25. What is the confidence? 100%. But that doesn't mean, even if X not then Y, if not X then Y, what is the support? 75%. Confidence 100%. So I'm saying if X then Y, if not X then Y. What's the point of the rule? You know? So that's where we are stuck. We need another metric, and that metric is called lift. Lift tells about whether the rule is correlation or coincidence. True correlation or coincidence. So the way you define lift is confidence divided by probability of P. So in this case, what is the confidence? 100%. What is the probability of Y? 100. So confidence divided by 100 by 100, 1. Lift is 1. Lift is confidence divided by probability of the right hand side. Right? Probability of confidence divided by probability of Y, which is 100 by 100, which is 1. A lift of 1 or close to 1 means it's a fluke. That's the way you interpret. You want only those rules that have higher lift. The higher the better. Essentially you want P of Y, the denominator should be as low as possible. If the P of Y is 100%, however confident you are, you don't care. Right? So more than Y is better. Less than Y, actually try the complement rule. If P of X then Y has a less than 1 lift, try P of not X then Y. If it's not guaranteed that it will be a good rule, but it's time for you to test it. As you will see, almost all rule generation mechanisms are greedy searches. So you are not guaranteed to find all possible rules. You are guaranteed to find one basket of local minima of rules. Right? So there is a very good chance that you have not found a good rule. And hence doing these kind of tests, if P of X then, if X then Y is a rule with a lift of less than 1, you try if not X then Y and see. Maybe your algorithm didn't try it. Maybe that's a jackpot rule. You found a great rule. So you will try that. Okay. But lift is another extremely important metric. So for this case, the lift is 1. And hence, I'll call it a fluke, coincidence. It's not a correlation. By the way, there's a lot of discussion in the data science community about science built on correlation versus science built on causation. We are actually doing all our work is on correlation so far. I am saying if X then Y, high support, high confidence, high lift, let's say, good lift. All I am saying is X is correlated to Y. If X then Y is actually not true. the statement is not true. All I mean is y is highly correlated to x. So it doesn't mean y is caused by x. Y is highly correlated to x. Then there are many people who question the entire science itself. How can you rely all your predictions based on correlation when what the world is seeking is causation? Does that make sense?
Yes.
There is a whole Columbia, they offer a program in data science, and one first whole class that lady had this discussion between causation and correlation. They fought and fought and fought. But think about it. If you go back to Vedic times in India, Greek, Plato, philosopher time, what was the method of knowledge derivation? How did they derive knowledge? Plato, Aristotle, or our Vyasa, Valmiki. What did they do to generate knowledge?
Observation and induction.
Observation and inference, right? So that was the valid way of doing science. Prehistoric till Galileo and Newton messed it up. Right? That was how people learned. They looked at a few data points and they said, oh, the king died and his father died and his grandfather died, so all men are mortal. Right? They looked at a small part of observations and they generalized it. That is called inductive learning. Inductive learning is where you take the data, make some observations and generalize it to the whole. And then 16th century comes 16th century, Galileo and Newton said, no, this is not the way to do science. You are allowed to create extremely small number of such observations. About any field, you are allowed 3, 4 max such observations. After that, anything else that you postulate, you should be able to derive from these 3 or 4 things. And you know what? I give you this great tool called calculus to derive, or mathematics called derive, and to derive. But that is what Newton and Galileo said. And then they said, once you derive it, you experiment and use your experiments only to validate your theory. You can't generate a theory based on experiments. You use experiment to validate a theory. This is called deductive learning. Deductive learning, start with a few hypotheses. I will live with it if you don't have a proof. Newton said, I have 3 laws, which I can't prove. Maxwell said, I have 4 laws of electricity, I can't prove. Quantum mechanics, Heisenberg and de Broglie said there are 3 or 4 laws. So, there's no certainty, and then whatever, matter has a wave form and wave has a matter form. That's it. Rest has to be developed from there. Right? So, thermodynamics, 3 or 4, 3 laws of thermodynamics. So, any field from then onwards, you are allowed to make only 3 or 4 hypotheses without a proof. After that, anything else that you say has to be mathematically derived from these 3 or 4, and you use experiment only to validate. So 16th century to mid 1950, inductive learning was killed by deductive learning. People, in fact, even today, ridicule inductive learning because Indian astrology is ridiculed. I'm not getting into whether it's right or wrong. All I'm saying is Indian astrology is an inductive science. Well, I can be short for calling it a science. Indian astrology is an inductive art. Okay, whatever it is. But there, you saw someone who is born on the mid-afternoon of May becoming a king. You observe 150 of them. You build a rule that there's a 90% probability that if someone is born on a mid-afternoon to a royal king, when the Venus is there, then he becomes a king. Right? Now, 90 out of, there is a rule of 90% confidence with whatever support. That's the astrological principle. But obviously, inductive learning was not allowed, accepted. So 1600 to 1950, deductive learning was the king. Then came, interestingly, deductive learning failed to solve even a 3-body problem. Forget about n-body problem. 3. Newton, all our IIT problems, one body hits the other body, you did all the friction and you remember that pulleys and all that we can solve that. What if there is a 3rd body? You should start simulating. Right? It gets too complicated. So people said, this is wonderful for enhancing our understanding, but for solving real world problems, I need a different technique. So they started simulations. And then simulations started failing. And then people said, oh, you know what, let me not worry about why they are happening. Let me look at data and make some inferences. Exactly what Plato did. Only difference is, Plato worked on 100 records at a time. We are now working on 100 million records. So we are doing inductive learning on much larger volumes of data. And Plato had intuition, Vyasa probably had the tapas and intuition. They used a different technique to extract the rules. We use mathematics to extract the rules. But essentially what we are doing is inductive learning, which to many is not even a science. But intelligently the computer science community had added enough math in it so nobody can question it. So we listen to the data using math. That doesn't make it a true science. In the deductive sense. Okay, so there's a lot of arguments on this thing. Just don't ever get into that. We are doing correlation, not causation.
So this lift, we can have a rule where my lift is greater than 1, a good lift, but my confidence is like 50 or 40.
Exactly. So then it is back. We need to figure out. So this is the problem, right? I have to now design a rule based on support, confidence, and lift.
So then we are not using only lift as the method.
No, we are not. We use all three. In fact, it's not over yet. We use several more. But in correlations, at least 3 metrics are needed for me to be comfortable that I can rely on the knowledge that I extract. Support tells me how much of knowledge am I gaining. Confidence tells me how confident about the knowledge that I am gaining. Lift tells me whether my knowledge is fluke or true correlation. Right? Good. So, this is the interpretation. You want lift greater than 1. How do we know the minimum support? Let's think about it. So, first question is, given a basket of rules, now I measure the support. What is the minimum support? So, I worked on an interesting way to handle it. Domain expertise never helped me, folks. Domain expertise never helped me. In the sense, nobody was able to really give me a good answer on, 0.2 is the most relevant support. So what I did is applied the central limit theorem to my advantage. Okay, I'll show you what I did. So this is y, xn, x1. So I have x1 to xn and some data. Right? I computed the support of the data. I computed the support. This is the right data. Now, what I did is, I randomized this. Right? So, what do I mean? I just mixed it up. I just put this record here, only y. This here, this there, like that. I just messed it up completely. Okay. What I have is junk data. Right? Obviously. Fake data. Now, on fake data, I ran decision trees. Or whatever, the rule inducer. Whatever rules I induced. And now I got support of those rules. Various rules I generated, I got support. Now I took the average of those supports. Mean fake rule support. Right? I got. Now, I took the original data and I ran a Monte Carlo simulation. Essentially, I created 1,000 fake sets. Right? I created 1,000 fake sets. And I created 1,000 rule inducers on top of them. I got 1,000 fake rule data sets. And I took 1,000 fake averages. My central limit theorem says that these average of averages will have a normal distribution. So all these average fake rule, average support of the fake rules will have a normal distribution. And not only that, now that I have a normal distribution, I compute sigma of these fake rules and I compute the mean of these fake rules. And now I know that If a rule has mu plus 3 sigma support, it's an outlier in the fake rule, and hence it's a good rule. Right? Pretty cool, I thought. You know, it's a very interesting way. I don't know if I was if I was in academia, I would have, true academia, I would have published it. But I haven't seen this anywhere. But it's a very cute technique, actually.
That could be random also.
What could be random?
Because since we are taking up by
Exactly, that's what I'm saying. Population, I can generate randomly any sample, and the averages of those samples will be a normal distribution. Is what my central limit theorem says. So I don't care. In fact, I want it to be random. I generate hundreds of random data sets, and the averages of those, and generate rules. Averages of those data sets will form a normal distribution with mu and sigma. So mu plus 3 sigma then tells me what is the most likely outlier for non-fake rule. So that tells me what is the minimum amount of support I should have for me to believe that it's not a fake rule.
Yeah, we can say that it is not a fake rule, but you cannot say.
If it's not a fake rule, if it's not a fake rule, that is the minimum support I can start trusting, right? Is there an issue there?
For example, suppose 5 values are 1, 2, 3, 4, 5. I randomly jumble them up. 3 remains same, the 4 comes down, and 2 goes up. Something like this. So,
I randomize it as much as I
yeah,
can.
yeah. So, now finally when I get my averages and make my rule. So,
And the other way, then you make rules.
yes. So now my outlier, suppose here now it is coming 1. So in another random experiment it can come 2 also.
Exactly. That's what, they are all normally distributed. You don't get a single value, you get all over the place. From that I am computing the distribution of fake rules. And hence I am claiming it's not fake. Whatever is an outlier to this on the upper side is not a fake.
By the way, what we can test in this hypothesis is the mean of the actual model, the mean of the support of the actual model. We can test the individual values of support.
Exactly, oh yeah. Mean only I will support, mean only I will take, right?
So you will take mean of all the 10 rules or 15 rules which you have created and test whether it's significant or not.
Oh, no. What I am saying is that the,
Because what we did is,
Yes.
we created, suppose we ran a one take out, we ran 10 simulations.
Yes.
Each of the times, suppose it had 15 rules, we are getting mean of the support of all those rules.
Exactly.
That's what
So
follows.
average of average supports. So the average support, the fake this thing, and the
The actual.
average of the fake only is what I am computing, right? I have created 100 fake sets. Each fake set has an average set of supports, and I have taken average of that. So they followed a normal distribution. Now what I get is the upper limit of the average fake support.
Upper limit of the average support.
Fake support. So anything that is beyond that is not an average fake.
But then we are not comparing average to average, because here it's the mean of 15 rules in each of those
Yeah, it's
scenarios.
an average of the.
Whereas here, the actual model is calculating mean and then comparing. We cannot compare.
No, but that's okay. But all I am trying to say is the average fake support cannot be any more than this value. So now you could say how I could interpret is if I had generated 200 rules like this, whose average lies around this thing, is it fake or not? Any rule that I take, is it fake or not? You know, with a small standard deviation. That's good. So that's an approach that I use for support, minimum support. So if the domain expert gives, great. If the domain expert doesn't give, this is a very interesting way. Statistically, you can find. So I am now interested in only those rules that have a support more than that, but a support less than 0.5 or something. But again, it's not a linear function. The higher the support, the better the rule is not right. You know, because very high support means it's a fake rule. Similarly, for confidence, confidence, I use something called z-score. And well, what something called z-score? We all know what z-score is. Now, all I'm saying is, if fundamentally it's very simple. For each class, I create the null rule. If nothing, then this class. Prior probability. If nothing, then this class. So if there is a data of 0.8 and 0.2, 0.8 bias and 0.2 non-bias. If I add a rule that says, if nothing, this non-bias, it's a 80% confidence. So I better get a rule that's more than 80% confidence. It doesn't make any sense if I have a rule that's... Similarly, for a non-buyer, I better get a rule that's more than 20%. So my z-score essentially is where the prior is what I make as 0. So I put a z-score with respect to the prior probability. And again, the ones that have more than 3 are fantastic. Between 0 and 3, yeah, it's okay. But anything less than 0 is not acceptable. Right? So confidence should be more than the null rule confidence. Support should be more than the fake rule support. Lift is simple, greater than 1. Now, one of the exercises that I have for you guys is, being an engineer, I want to have a simpler term. One number that tells me whether this rule is statistically good or not. I have given you support, confidence, lift, z-score, q-score. And I have given the behaviors. The behavior is support should go something like this. Very low support is not accepted. In fact, do we agree if the support is something like this? Below minimum support, it should be, it's no good. Importance, if I'm looking at importance as the y-axis, if it's below the minimum support, there's no importance up to a certain level. After that, it goes up and then it goes down. Confidence, similarly, up to z-score, it is unimportant, and from then it's a linear function. Lift, greater than 1, up to 1, it's no use. After that, it should go up. And after 2 or 3, I know it's correlated and not fluke. And then it should just sort of taper. It's not that the rule of lift 9 is much better than rule of lift 10. Rule of lift 2 is much better than rule of lift 1. But rule of lift 10 is not much better than rule of lift 9. Then you know Q scores and Z scores. Try to come up with one single metric, which is the goodness of your book. Take all these into account. Exercise 1. You can team up and do these things. Okay. In the lab sessions, try to do it. Okay. There's no right or wrong answer here. There's no published work. So come up with some interesting things. Okay. Good. But these are all the statistical metrics. What do you think is by the way, just one question. I am looking for a function that is 0 at 0 and 1 at 1 and 1 at infinity, asymptotically. 0 at 0 and 1 at infinity. Or even, let's simplify the problem. 0 at 0, 1 at 1, but non-linear. 1 at 1, but non-linear. So it should just go up like this. What is a good function?
X squared. X squared.
Root x. Root x is probably, yeah. I'm just, interestingly, where
Shift the circle at center 1, use the part of that.
I was thinking of sine or circle or
X
something.
minus 1 whole square plus dash.
That's why I was thinking of somehow manipulating a sine curve also. 0 and pi by 2, it goes up like that, right? Yeah. So where I was coming from is, I'm working with Dun and Bradstreet on understanding what makes language complex. Okay. Interestingly, there is a lot of study on how to detect spelling, mistake. In Microsoft Word, your smartphones have a spell detector, machine learning algorithm. where it looks at something called minimum edit distance. Essentially, if I change my letter, how many edits I have to do to get to a known word. But I didn't find any published work on how much a spelling mistake complicates our understanding. There's no published work. Yes, I can detect if it's a spelling mistake or not, but does a spelling mistake make life difficult? If so, by how much? Quantitatively. I didn't find it. So,
Why do we need that? Why do we need that?
good question. And why do you need to do any research is a very interesting question. You are at some level, I'm seeking truth. I mean, it's a fascinating problem to work on. But having said that, Dun & Bradstreet, their business is they collect enormous amount of data. I mean, probably they have a data not on a company like ZS Associate. They try to collect data on Naniwala pawn shop, right? And they collect this data about every possible company, billions and billions of rows of information. And which means in the past 10 years, enormous amount of social media data, right? So they need to sort these and automate these and do things. So it's extremely important for them to understand the text that they are collecting automatically, right? So what complicates understanding is a very important thing for them to know. And literature identified that spelling, grammar, sarcasm, neologism, new words are some of the factors that complicate language. Now, great, how much it complicates? So if I misspell elephant as elephant, just last word instead of T I put a T. I mean, you're not confused, man. You can still understand, and so can a system most likely.
On Twitter, we always use short forms.
That is neologism. It's a different problem. So that's not even a spelling mistake, LOL or whatever. You know, my niece sends me sometimes WhatsApp message and no word I understand. But that is neologism problem. Let's treat that differently. We are treating that differently. Let's take pure play spelling mistake. For cat, I spelled it as dat.
So there's like something called two-letter words. Sometimes the I skips those letters, right?
Yeah. So how much it complicates? So interestingly, I didn't find any computational linguistic literature where they had a formula for if you have 10 spelling mistakes, this is the amount of complexity of understanding.
So this is
Autocorrection works like this.
I know. Autocorrection works on detecting a spelling mistake. It doesn't tell you how complicated understanding had become.
But the understanding factor will be very specific to a, let's say for us, right? So there has to be a manual.
Oh no, but that's so we are now struggling to build a system. So we arrived at two metrics. One is called typo density, which is in any sentence we are just measuring how many typographical errors are there, and that divided by total number of sentences. That is the average typo density of a sentence. Now in the document, average of these average typo densities, that is the typo density. Then typo severity. From this word, how many edits I need to do to get to the right. So if I made one letter thing, it's a problem. If I change 2 letters, it's a bigger problem. 3 letters, it's even bigger problem. But typo severity, now what we realized is has a weight based on at which location of the word I am making the typographical error. In beginning and end are not very important, I believe. Middle is more important. So there is some research done on it. So typographical severity is the second thing, but it's a deviation. We don't need to do in this class. I'm just telling you. Now, what we are trying to figure out is given these two numbers, how do I systematically actually come up with? Ideally, my scale should be 0 if it's a pure text, 1 if it's a bad text, right? Horrible. Every word I make a largest possible error, right? Then it's 1. Perfect, no error text is 0. We are struggling to build a single number that represents it. So one of the things, actually I like that approach. One of the things in data science, some problems is you have to start deriving the metric itself. So the challenge that I have for you guys is, give me one number which takes support, confidence, lift, Q score, Z score, everything, But for your business user, ultimately, it should be, hey, the goodness of this rule is 0.896. So on a metric, 1 is great, 0 is, you have to put the upper bound and lower bound when you are doing these things, right? So the best rule should be 1 or 10, whatever. The worst rule should be 1, if it's a page rank kind of thing. Come up with one number. There's no published literature. You can trust me on that. I searched every possible paper on this. So come up with one metric, and I will plagiarize it and steal it. I'll use it in my paper. I'll reference you. If you have a better metric, definitely I'll reference you. Okay, but that's a good exercise. Try to arrive it. Now, everything that we learned, we started a bit late, or when did we start? Okay.
Decision trees is so widely, there will be some metrics and people will be.
No, people independently measure support, confidence, and lift.
Can you use it as a transition kind of system, like what is to find out mod of X, Y, Z?
Do that. Tell me. Come up with a reasonable thing. But the problem with is the support, as we learned, very high support doesn't mean it's a better rule. So I should come up with, first I should arrive at support importance, which is a sinusoidal curve. It peaks in the middle. Confidence is linear. Lift is a asymptote.
Polar system.
Polar, do it, I mean, I'll say come up with something. There's no right answer. Yeah, polar system is I don't know. I mean, I used a sinus. I would have preferred a
I
sinusoidal.
would account in that issue. Polar system would account in that.
Yeah, but for lift you have to do an asymptote. It goes and then after that it should become thinner and thinner. The improvement. Initially, 0 to 1 is a huge jump. 1 to 2 is a huge jump. 2 to 3 is a huge jump. Actually, 0 to 1 is no jump. 1 to 2 is a huge jump. 2 to 3 is a smaller jump. 3 to 4 is even a smaller jump. N to n plus 1 when n is large is infinitesimally small. So come up with an asymptotic function and inverse cosine function and linear function and combine them in a meaningful way to give me a scale. But it's not a trivial thing. I'm sure you need to put in enough time.
Assuming that people do this exercise manually by analyzing all the
Yes, exactly. They look at all 3 metrics and manually arrive.
So there's a 500 roots and you have to look at.
Oh, yeah, exactly. Exactly. Even this is not adequate. Even if you come up with a number, that only tells you statistical goodness. So we now want to talk about non-statistical metrics also. Another thing that non-statistical goodness of a rule is, actually, should we take a small break? What is the, we started at 8:20, right? Let's take a small break. When you come back, I want to talk about non-statistical goodness. But yes, people do not have a single number to measure. There's no R square. I am unable to optimize nowadays. It is getting crazy. Where is it? But next 3 days, next 4 days are going to be fairly light in the math thing. So you can, yeah, you have to be there for the 4 hours, but it won't be as troublesome as probably your kernel regressions are. No, you don't do Gaussians and add them with different weights. You don't do those things. There is a little bit of beautiful math, but I don't think it will be anything to worry. Anyway, let's get started. Others will join. So far we looked at statistical goodness, right? Support, confidence, lift, and what is Q score? I call that minimum support Q score, minimum confidence Z score. Combination of all of them is one number that we need to derive. Now, I want to talk about a few business metrics. All these tell us statistically how good the rule is. Business-wise, I'm always worried about what would be more exciting to a business. So, I think I talked about this example some time back. So I was working with the Chicago, some medical system, and the challenge there was to extract a pattern that the doctors didn't know about the probability of them catching asthma, right? The kids. And one rule that we extracted was if the mother's blood group is B positive, sorry, it's actually father. If the father's blood group is B positive, and the mother smoked during her pregnancy, and the kid is eating a lot of carbohydrates, then the kid is likely to get asthma. So if the father's blood group, let me write it correctly. So this is a rule, a prepositional. If the father's blood group is B positive and mother smoked during her pregnancy, and the kid is eating a lot of carbohydrates, then he or she is likely to get asthma. He or she is the kid here, not the mother or father. Now, let's say this rule has pretty decent support, very high confidence, high lift. Let's see, let's issue. Yeah. So, still, let's look at it. What can the system do about the father's blood group being positive? I mean, the idea here is whether they can cure asthma or not. How to cure asthma? They are also interested in curing asthma. So the doctor can't do anything about the father's blood group. The doctor also, can anything be done about mother smoking during her pregnancy? For that kid is born, for that mother you can't do anything. For that mother it's over. But at a strategic level, you can probably set up a hoarding in places where you have teenage girls who are smoking, who are likely to have colleges, etc. You can put some hoarding, so in future you can save. But for that kid, there is no action to do. But the kid is eating a lot of carbohydrates. You can tell the kid, no more French food, French fries, no junk food. Today onwards, cabbage, carrot, beetroot. Live like a rabbit.
Explaining this to
You may not even explain, but you can take an action, right? Right. So, what I am interested in when I am generating a rule, one thing that I am really interested in is observing whether the data offers me any clues to transform an undesired state to a desired state. So, in my product, what I first do is I ask the business user, what is your desired state, what is your undesired state? If it is a fraud, not fraud is desired, fraud is undesired. In this case, no asthma is desired and asthma is undesired. Customer is desired, no buy is undesired. So the person defines what is the desired state. Now, what I do is when I get a rule, I want to automatically perturb each of the attribute. If x is equal to x1, x2, x3, then y. Can I change this x1 to some other value? Can I change this x2 to some other value? That makes me see once I go to the other value, is the right hand side changing from no to yes? So if the kid is not eating it, let's say I move it down to not eating a lot of carbohydrates, then what is the new rule? What is its support confidence lift? I hit a jackpot if it becomes no asthma with a high confidence. Right? So what I do is I take every rule and I try to perturb the attributes and see whether the outcome, the right hand side, changes to a desired state with high support confidence lift. If that happened, you hit a jackpot. This is a nice what if scenario. Okay. So one of the things that I would like you guys to do, I mean, There are many things that I will set a reasonable homework. This is one thing. Just note it down. Let them pick. Given a rule, they should be able to automatically perturb, write a for loop, perturb, check the new rule support confidence lift, and see whether it transforms the state. If so, does the data offer any clue of how to transform a bad customer to a good customer? Right? So that's a very powerful, no known tool that I tested, SAS, SPSS, base R, allows for this. You have to manually write the code, or you have to take them into Excel and then manually do the filtering changes. That's why I had the code written in my thing, but it's not a difficult code. You can write it. Now, while I'm writing this code, one question that I want to ask is: there is no way for the system to know that father's blood group cannot be changed from B to A. I can't change the father after it's over. That's it, right? So similarly, mother's thing in this case I can't change. So I asked the user to define what are actionable attributes. Just as important as a numeric categorical ordinal, I asked the user identify actionable attributes in your data. If it is a sales, maybe discount is actionable. The mode of contact is actionable. Am I calling him or am I talking to him, etc. So actionability is, this is a term that I defined, is the ability of a business user to change the value. So the gender of my customer, I can't act on. Whereas the discount I am giving to my customer, I can act on. So I ask them for actionability, and now what I do is whenever I have a bunch of rules, I compute the actionability of the rule, which is number of actionable attributes on the left hand side divided by the length of the rule. 3-length rule or 4-length rule, number of things. And I put highly actionable rules at the top. For me, the thing that I focus most on is highly actionable rules whose right hand side is undesired state. Because my goal as a business user is how do I transform a bad customer into a good customer. So I'm really not interested in rules that are talking about good customer as far as acting is concerned. Because I don't want to transform a good customer into a bad customer. And no business user is interested in that. So highly actionable rules with lots of attributes on the left hand side divided by length of the rule. So that's a normalization thing. Who are talking about undesired state. And now I run an auto for loop where I try to change the values of each and every actionable attribute and see whether it transforms into a rule where the Y class becomes desired and still decent support confidence in lift are maintained. Does that make sense?
So in this case, we can try reducing the length of the rule and we can drop the father's blood group part.
We'll come to that. That's one. Okay. We'll just hold on to that thought. I'll talk about that.
From the data perspective, suppose we had 100,000 records, we took 50,000 records and created suppose these rules. And then we would tweak the actionable parameters in the other 50,000 records and see how does the...
No, even within these 50. So in these 50, I said if kid is eating carbohydrates, then he has asthma. I look at the data where kid is not eating carbohydrates. If I change it, now the filter moves to some other zone.
So now all the values will change about...
Everything else I keep constant. So mother's blood group, father's blood group is B positive, mother is smoking, kid is not eating carbohydrate. This is a slightly different subset. What is the Y in that? If it is a rule with 90% probability that there is no asthma, I hit a jackpot. Then I go to the doctor and tell them, hey, you know what, if you prescribe less that this kid should not eat carbohydrate, the data says that there is a very high likelihood, given all other conditions, that he will still not have an
You are
asthma.
saying the entire data of 100,000 records. After we get this rule, we find the records which follow the other way around.
Other way around. And whether see that has enough support confidence lift for me to be confident about that behavior. If so, I hit a jackpot. So think about knowledge,
By default, the other rules also would have existed when we created.
but it may not have enough. With all the conditions met, The other rule may not have sufficient support confidence lift. Again, I believe a rule only if the statistics are good. So you are going to give me one number. The rule goodness is 0.9, let's say. These conditions tell the rule goodness is 0.9 on undesired class. I change this. The new rule, if it's 0.7, I'm great. If it's 0.001, I don't care. So think about knowledge in 3 dimensions, right? The what of knowledge, the why of knowledge, and the how of knowledge. Okay, what is the status? Is he an asthma guy, or will he not have asthma? Will he have asthma? That is not explicable. It's only a prediction. I am saying this guy will not have asthma. This guy will have asthma. That's the lowest form of knowledge I can get. Your prediction, neural net, kernel regression, any non-linear model you use, you get the lowest form of this thing. The second is why of knowledge. Why is this kid not having asthma? Your logistic regression and your decision tree actually have the capability of giving you that why. Logistic regression gives you by coefficients, and decision tree is even better if then rule. Then is how do I convert a bad guy to a good guy? That's the highest form of knowledge. That's jackpot. If I hit it, it's a jackpot. And the logistic regression, you do it with sensitivity analysis. You try to move the attributes this way and that way and see whether you get the optimal thing. Here, again, it's a sensitivity analysis. You move it up and down. Each actionable attribute, you move it up and down and see whether the outcome changes to a desired state. And does the data offer enough clues? In the sense, enough support confidence. But one thing that baffles me is this whole actionability business itself. This is only a sufficient, it's necessary but not sufficient. See, in the sense that I was reading somewhere about this Obama campaign. Obama campaign said that last election campaign, what they identified is women between 35 and 50 age group who drive morning and evening to the office actually are the ones who keep changing their decisions between Republican and Democrat. So if you attract them to vote for you, there's a high likelihood that even if they were previously supporting Republican, you can actually convert them. What are actionable attributes here? Women? No. 35 to 50, that's their age. They drive to the office in the morning and evening, I can't act on it. On any of them I cannot act. But actually, they found that is the most actionable rule because they then decided for Massachusetts, where they found this pattern, they said for the caucus, they took George Clooney as a guest, dinner guest. George Clooney is that handsome hunt, right? The Ocean 11 guy, right? So if you want to get many 35 to 55 women to attend the dinner meeting, you better have George Clooney, not Warren Buffett. Right? So it became actionable. How do I know computationally that that's an actually actionable rule? None of the attributes are actionable. So that tells me that is a segment that I can focus on. So there is always a segment on which you can focus on to do something. Okay? And at least I couldn't figure out any data science way to figure out which segment. Essentially, each rule is a filter. Collection of multiple filters. So I am segmenting the data. You can think of these as micro segments. I couldn't find any way in which I could figure out which segment is more interesting than other segment. Right? If there are 10 segments, all of them talking about non-bias. Is one segment more interesting than other segment? I couldn't find any machine learning ways of doing it. Whereas, machine learning way, if you define actionability, I can actually identify rules with highest actionability and see whether there are any clues to move it from one class to the other. So actionability is still one attribute that I compute for each rule that I generate, and I am really interested in high actionable rules that are talking about the negative class. Then the next step is understandability of it. Whether I can understand a rule or not. What do you think? What is the metric? Understanding a rule.
But suppose like for trial example, right? So you told also told that when you drive in this particular time they are working in. So now that is something which you can use, right? So,
No, understandability is how explainable the rule is. It's a simpler metric actually.
The length should be.
Length is a good
Some
in-
order should be like,
Is order very important or just length? Order is what?
sometimes is the
I mean, you talk about first order.
Oh, okay. Let's restrict ourselves to propositional rule, first order. You're absolutely right. Order makes it really complex, but first order small rules are more understandable. If x, then y is more understandable than if x1, x2, then y. If x1, x2, x3, then y gets more complex. As the length increases, understandability decreases.
how many
What should be the function then? How should I quantify understandability of it?
how many binary functions are coming out? Like for example that father boss is here. So
No, I'm talking about understandability as in, this rule is understandable.
yeah.
This rule is less understandable than if I added one more end here. That's all I'm saying. Not action. Actionability is already we looked at. Understandability is length. I agree with that. All I'm asking is what is a suitable function? Longer rules are less understandable. What's a suitable function? It is not a trick question or is it a trick
It
question?
shouldn't be too short as well.
Exactly. Give me a formula.
So it should be like again a parabolic thing. Like
No, in fact, it should be as short as possible, right?
no, if you give too less information, I cannot understand at all.
Understand why? If age is young, then they buy. Young people buy. It's an easily understandable rule, right?
Yeah, you gave that example, right? The CC average is median.
Medium then. So what is give me a formula?
1 by n or 1 by n?
1 by L. 1 by L.
1 by n square.
1 by L square. Okay.
Number
How many of you agree? 1 by L. Understandability is 1 over L. L is the length of the rule. Left hand side.
No.
But yes or no? No. Why no?
I mean, how much quantity of information you are transferring is that?
All I am saying is understandability. I am not talking about quality of the rule. That's a separate metric.
So because when we say understandability, when we are saying only one, suppose the length is only 3 or 4 words. There
3 or 4 word, 3 or 4. Length is 2. Length is 1. All he is saying is length 1 is more understandable than length 2. Is more understandable than length 3.
For example, if the rule is like, if the person is tall enough, he plays good basketball. So that is understandable. But if the rule is something like he belongs to this area, then he plays good basketball. Maybe I cannot understand it business-wise.
No, you may say it may not make sense.
But it's to understand.
That's not what. You can still understand the rule. Understandability is understandability of the statement. Can you understand what the guy is saying? So what he is saying is if the guy belongs to Nagpur, he will play better basketball. You may say it doesn't make any sense, man, because you understood it. But on the other hand, if I say if the guy belongs to Nagpur and then lived in a concrete house and went to this particular school and is between 5 and 6 feet and has 3 brothers, and then it gets more and more complicated to understand. So why are you not agreeing to 1 over L as a measure for understandability? It's correct. Now, think about 1 over x. I made the same mistake. 1 over x is a function like this, right? That's a rectangular hyperbola from past birth. Huh? Right? So 1 over 1 is 1. 1 over 2 is 0.5. 1 over 3 is 0.33. 1 over 4 is 0.25. So what I am saying is the understandability drastically drops down from 1 to 2. The drop is slightly less from 2 to 3, even less for 3 to 4, even less for 4 to 5, and after some time it doesn't work. But in reality, that's not how the understandability is. If anything, the understandability should be dropping. It should, 1 to 2 is actually less complicated than 2 to 3, and after some time it should actually asymptotically. So I would have a point of inflection. Tell me whether it makes sense. That probably is a better behavior. So find a function for me. Find a function that does like that. A good exercise. And refresh. Go back to your color sketching, 11th grade mathematics, and figure out a function that behaves like that. And maybe it can be a discontinuous function. You may want to define it up to this point. It's like this, then it is like this. Just have fun. Okay. Right. Then comes triviality. So does it give me enough information or not? What do you think is a good metric? Triviality is definitely very short rule, could be trivial. Sort of inverse of this. If a rule is very short, a young man, I probably know that already. High support, high confidence, short rule. Do you think the guy already knows it? The business user? High support, high confidence, short rule. Would the guy know it already? Probably. So arrive at triviality. So actionability, understandability, and triviality are a few things that I try to define and metricize. So there are 4 or 5 statistical metrics: support, confidence, lift, G-score, Q-score, that minimum support thing. And then actionability, understandability, and triviality are the things that I want to define. I want you to now come back to me with right metrics. And one exercise that I want to give you is write your thought process on how to describe the goodness of a rule. Ideally, one way is actually arriving at a single number. Using all these, you arrive at a single number. The other way, you say, no, that's very, very weird to do. One of the things that I do is I actually draw it as a chart. Support, confidence, and then I have lift. Lift is represented by the size of the rule. Ideally, I want a big circle, which means high lift, that's on high level because high confidence, and somewhere in between, a range in support. So big bubbles that are hanging high in a region is what I'm interested in. So you can take a graphical view. But think through, there's no right or wrong answer. What I encourage you is now you know a whole bunch of metrics. Support, confidence, lift, minimum support, minimum confidence, actionability, at least I defined some form, understandability and triviality. With all these, tell me how, if I have given you 500 rules, how do you prioritize them? How do you tell me automatically which 10 are the most exciting, most likely? These are the 5 or 10 that you should look at, right? Think through, and that's a good exercise. Any questions on this? Now, one point that you mentioned, I asked you to hold on that thought. Again, most of the rule generation mechanisms that we are going to learn, in fact, almost all that are popular are greedy approaches. So, you are not guaranteed to find all the rules in the data, or you are not guaranteed to find the best form of the data. So, one more thing that I do is the process called generalization and specialization. Whenever I am given a rule, I try to drop one attribute. When I drop an attribute, I am lessening one more constraint, so I am widening the filter. Right? Dropping an attribute essentially is if x, y, z, then a. If x, y, then a. I dropped an attribute, so x, y is less constrained, so it's covering more data. This I call generalization because I'm generalizing the rule. And generalization typically increases the support and reduces the confidence. Right? If I'm covering larger data, yes, support is larger, but confidence may go down. So I am interested in generalizing in that way where confidence goes by the least, goes down by the least, but support goes down by the highest. Increase, support goes up most. So support by confidence should be as high a value as possible. That is the attribute with which I generalize. I have 10 attributes in a rule, which one I should drop? Dropping any rule increases the support, decreases the confidence. So I want that rule, that attribute to be dropped such that the support increases greatly but confidence comes down by least. So I'll compute the new support by confidence for all the rules. The one that is highest is the one that I pick. Okay. Similarly, specialization is adding a new attribute. So if x1, x2, x3 then y, as opposed to if x1, x2, x3, x4 then y. Right? I'm narrowing, I'm adding a new filter. So support comes down, confidence goes up. So this time I'll do confidence by support. The one that increases the confidence most but least drop in the support is what I want to, how I want to specialize. So any rule, you generalize, you specialize. Right? So interestingly, this is all I did. I enabled this post-processing of rules. I mean, I did some nice things to generate more rules, but ignore that. That's actually, you will be able to do 90% of what I did, and those 10% of the rules, even if you don't find it's okay. All I did was one tool which measured, in addition to support confidence lift, this actionability, triviality, and understandability, and it's enabled user to automatically generalize and specialize and describe them in graphs and do that, what if scenario. Automatically changed the actionable attributes and came up with clues on how to change a negative class to a positive class.
So generalizing is essentially marginalizing the probability.
Yeah, say that again.
Generalizing is essentially marginalizing the probability as such, right?
Marginalizing the probability of what?
So when we have like an ABC as the
Yeah, you are marginalizing on that attribute. Good. Yeah, you are right. Okay. No. When he said marginalizing, if I have P, A, B, C, when I generalize, I marginalize on C. I now only have P, A, B.
So you marginalize support by dropping C.
Yeah, you marginalize that attribute. You support is joint probability anyway. So yeah, you marginalize on an attribute. You are absolutely right. So I'm removing that filter. Right? So there, all I enabled is this post-processing. And now Pearson Education Group, Lockheed Martin, Chrysler, Caesars, Chrysler, all they have bought this product. So one way to build data science is actually not inventing new algorithms. There are already algorithms. There are already open source libraries to do that. Think how you make data science easier and easier for the business user, more relevant for the business user, and you typically hit a jackpot. And I was surprised when I built it. The institute, we got 4 patents. That was surprising. But anyway, generally publishing papers and writing patents is an easier part. But then someone came and said, you know what, we'll pay the institute money and we will actually give the institute the equity. I said, are you crazy? I mean, man, do you really mean what you're saying? They said, yes. And I said, okay, bakra banda hai. And then, I said, fine, even if you decide to do that, do it. They did that. Then actually, they went and they sold it to 4 companies. Now I feel bad. Oh, I wish I had asked for a bit more the equity. Why did I settle for 5%? But that's okay. Life goes on. But so that's a rule news to me that you really don't have to do enormously complicated mathematics in data science to be attractive. You just have to figure out how to make it that much more easier for the business user. All I did was, it automatically did all these rules, automatically searched, and came back and said, the four most important, most profitable actions that you can take to convert the bad guy to good guy is change this attribute to this attribute to this attribute to this. If you do this, there is a 20% probability that 20% of your customers with a 90% probability will become customers, non-customers will become customers. If you do this, 17% of your non-customers with a 85% probability will become customers. So it identified 4 actions. But you know exactly what I did now. I looked at every possible rule, I looked at every actionable rule there, and I saw if I changed whether undesired to desired transformation occurs, and so then it occurred. Right? That's the mathematics that went in. One last thing I'm now trying to implement is cost of rule. So this is included already in the previous works of Quinlan also. So let's say I have a rule that said, if platelet count is less than 20,000, there is asthma. Then if the density of the marrow in the bone is between 0.2 and 0.3, then there is asthma. Now the second rule has a 95% confidence, first rule has a 85% confidence. Which one is better? Platelet count, you just take this much of blood and you measure it. But density of marrow in the bone, you have to poke something into the guy's bone and then drill out something, and you are putting the guy through torture. Right? So is the extra 5% worth putting the guy through this much? So cost of acquiring an attribute is also a very important metric in determining how good the rule is. In fact, many people say the goodness of a rule is, we'll learn that, but here you can just add sum of the costs of all rules. And normally you identify not even exact cost, how difficult it is to correct this data. Low, medium, high, or on a scale of 1 to 5. Just you have a cost of collecting each one. Now, a rule that is less expensive is always more preferred. So that can also become a metric in goodness of it. So all I want to tell here is, just like in linear logistic regression, you have some statistical metrics, which are your support, confidence, lift, Q score, Z score. They tell you, like in linear regression, the p-value of this is low, q value or whatever, p-value of this is high. Like that, you have a bunch of attributes that are important. Similarly, for a rule, you can arrive at these statistics. Support of the rule, confidence of the rule, lift of the rule, the q score, z score, and all that. But at the same time, just like how logistic regression doesn't tell you, even if a low p-value doesn't make it exciting for a business user, something that slightly high p-value is more exciting to the business user. Here also, there's no way for you to know. The few things that I worked on are actionability, understandability, triviality, cost, things like this which have a business sense. You can take a look at all of them and come up with. So the exercise here is figure out how to represent the goodness of it, either as a number or as a chart. I want to give 2 exercises. They are divided into, for projects, they are divided into 4-member teams, right?
Yes.
3-member teams. So there are some 10 teams.
Yes.
So 5 of you can do one and 5 of you can do the other. Right? Our teams need not do both. You're welcome to do, but you don't have to do, right? Fine. So with that, we are now ready to start generating rules. So far, we haven't generated a rule. We only have talked about, if I generated a rule, how do I know whether it's good or bad? Right?
So in gateways, we are automatically generating rules after the probability, using the probability each level.
What rule am I generating there? I get a probability.
So using probabilities can be generated.
Very, very indirect process. So, because you give me a condition, I see whether the probability is low or high. Now, think about how many conditions I can generate. If I have 4 attributes, okay, each attribute having 3 levels. First one can be any of the 3, second one can be any of the 3, third one can be any of the 3, fourth one can be any of the 3. 3 into 3 into 3 into 3, 81. Now I have 3 classes. For the first one I can have all these 81. For the second one I can have all these 81. For the third one I can have all these 81. So that is 81 cube. Right? It's a huge data set. If I have m classes of m attributes of n levels and p classes, I am talking about p to the power of m to the power of n hypothesis.
But we get threshold as 3, right?
Huh?
81
81
into 3.
into 3. For the first one I can have all 81 possibilities. For the second one I have all 81 possibilities. 81 cube, right?
So we have 3 different classes of the Y variable, right?
Yeah.
For each of the class, I need 81 different records.
Yeah. 81, second 81 into 3. Yeah, you're right. 81 into 3. 243.
And even then, attribute probability threshold, right?
But I have to look at for 243 different rules, 243 hypotheses. I have to now arrive at first hypothesis, what is the support confidence lift? Second hypothesis, what is the support confidence lift? And then peak compartment. So even for 4 attribute system, I have a large number of rules. So you don't, so the answer to your question is, rule generation, exhaustive search is not the elegant way. You don't write all possible rules. Measure the support confidence of each one of them, either through name base or through this, and pick the rules that are important.
But here we have numbers so that we can put some link.
It's not about the ability to find whether a rule is good or bad. That's the easy part. The amount of computation that you do in describing each possible rule. So if I have 100 attributes and each attribute has 5 levels, how many rules I have to write? 5 to the power of 100. 5 into 5 into 5 into 5. 5 to the power of 100 rules you don't write. And if you write them, computing support confidence lift of our joint property is the easy part. But doing 5 to the power of 100 rules is not the elegant way to do. So you use other techniques to extract a subset of rules and only measure for them which is good or which is bad.
In this case, what is speaking about time space, what we would do is we have three levels in the Y attribute, right? I would calculate P of, so I would calculate P of each attribute given all these parameters.
Well, all those, so that's why, right? P of y given A, B, C, D.
All of them.
How? So computing a probability is not the issue. First, writing all the
In
probabilities.
this case, I don't have to write. I have to do a test data.
Now, if I gave you a condition, that's naive Bayes. What he wants is not a condition. What he wants is I gave you a data set, come back with all relevant rules. That's what he's asking. If I told you, if CC average is this, age is this, income is this, will they buy or not, that's regular naive Bayes. I'll get probability. He's not asking that. I will give you a rule, a data set. Write the probability, do a pre-naive Bayes on every possible condition. Look at whether it's good or bad and make it a rule. If it's good, Y is good. If it's bad, Y is bad. The probability that argmax. So what I have to do is for every possible condition, I have to compute argmax of good and bad and then assign a class and come up with the rules. And then I measure the support confidence and yield. That's a
So
humongous
we
list.
need not do that because
We don't.
in time space we don't need to create rules.
No. What he's asking is, can I use naive Bayes to extend this as a rule in user? No, you don't. Okay. Right. Now, the first technique is perhaps the simplest of the lot, called prism rule. Okay. Very, very simple. This is also called divide and conquer. Okay. This is called separate and conquer. Separate and conquer mechanism. So, I have taken a toy example. This is a bit difficult to read. So essentially I want to figure out whether I want to not recommend a lens, contact lens, or will I recommend a soft contact lens or hard contact lens. None, soft, hard, 3 classes. And there are, age is one criteria. spectacle prescription, myopia, hypermyopia, metropia, hypermetropia is one thing. Astigmatism, no or yes is another thing. Tear production rate is the next. Right? There are 4 attributes. Age, sorry, I'll read it out for you. It's a bit difficult to read. Age, spectacle prescription, astigmatism, tear production, and finally I want to decide whether I'll recommend a lens or not. So now my goal is to generate rules. Okay. What we are going to learn is the simplest of the mechanism, but it actually works very nicely. Extremely simple logic. I will start with a condition. If nothing, then recommendation is one of the 3 classes, hard or soft or none. I'll randomly pick hard or soft or none. Okay. So for this thing, now this question mark can be age young, it can be young, pre-presbyopic, presbyopic, and then it could be prescription is myope, hypermetrop, whatever, myope or hypermetrop, and astigmatism is no or yes. Tear production rate is reduced or normal. It could be any of those. So how many I have to try? 3 plus 2, 5 plus 2, 7 plus 2, 9 different combinations. Oops. So I tried, age is these 3, spectacle prescription is these 2, astigmatism is these 2, and tear production rate is these 2. So what I am saying is, if age is young, then recommendation is hard. If 2 out of 8 records, that is the confidence. The confidence of this rule is 2 by 8. If age is pre-presbyopic, 1 by 8. Age is presbyopic, 1 by 8. Spectacle prescription is myope, 3 by 12. Hypermetrop, 1 by 12. Astigmatism, 0 by 12. Astigmatism, yes, 4 by 12. Tear production rate normal is 4 by 12. Amongst all these 2 are the winners. If astigmatism is yes, then recommendation is hard, is a rule with a support of 4 and confidence of 33%. Same is with tear production rate. Support of 4 and confidence of 33%. Does it make sense? If I tried all possible 7 values here and I pick one of these 2 are the best. Does that make sense? Yes, sir. I mean, it's a fairly straightforward logic. Try all possible things and pick the if rule. Now you have 1 length if rule. So you grow the rule. You start with 0 length. Identify the best guy to fit. Best candidate for the first length rule. Best candidate for the second. Then you have the best. Now randomly pick one of these 2. Astigmatism or tear production. Let's say I picked the astigmatism, yes. I picked this one. No specific reason. I could have picked this one also. I picked this one. Astigmatism, yes. Now I have a subset. This is a 1-level rule which says if astigmatism is yes, then recommendation is hard. It has a 33% confidence and 4 support. I set a pre-limit. I will generate only those rules that have 80% or more confidence or 75% or more confidence. So I still don't have enough confidence. Now, I will now try out if astigmatism is yes and question mark, then not. My rule is if astigmatism is yes and question mark, then recommendation is hard. Now I try with age is equal to young, presbyopic, pre-presbyopic and presbyopic. Spectacle prescription is myope or hypermetrop. Tear production is reduced or normal. I try all of them and clearly tear production rate is normal is the winner. There's no confusion here also. This guy is the best. This guy now has a support of 4, confidence of 4 by 6, 66%. So if astigmatism is yes, tear production rate is normal, then recommendation is hard. I now filtered based on these 2. Is it enough? Good enough. I have a support of 6 and a confidence of 4 by 6, 66%. If it didn't meet, I will now continue.
So by the way, we are changing the denominator by calculating the confidence.
Exactly, on the filter, right? On the filter only. Yeah. At every point, what is the best confidence, best support?
But this rule in the the entire data would have very less confidence.
It'll be, why would it be any, okay, it'll be less confident, but in this process I can't find a rule with better confidence. That's all I'm saying. Right? Now, but by the way, it will be the same confidence, 4 by 6 only. My left hand side is, what is my confidence? P of B given A. Given A, there are only 6 records. Given A, and I'm conditioning on it. A is the left hand side. Exactly, yeah. So now I'll go by, again, young, presbyopic, pre-presbyopic, myope and hypermetrop. When I try that, age young this much, I pick probably spectacle prescription is myope, because though both of these have 100% confidence, this has a higher support. So I'll say, now my first rule is, if astigmatism is yes, PO correction rate is normal, and prescription is myope, then recommendation is hard. I got 3 records that obey that. Now I separate those 3 records, restart the process.
So we did not encounter case where we have a conflict between support and confidence. Then
Then you put a rule.
personal.
You could put a personal rule. Interestingly, R doesn't have a library to do this. So I want you guys to build it. Simple enough, right? As a group. That's why I said you don't have to do both. Pick one of them, but ensure that both are built. But there's no library in R. I would have. There is a library we didn't look at. There's a tool called Weka. W-E-K-A, Weka. That has a library built in. It's a Java-based thing. It's like R also has an integration integrated to Weka. Weka used to be very popular before R, but R sort of took over. So, you can write from ground up. It's a bunch of for rules, but you shouldn't apply for rules, right? You have to do only the what do you call them? So the applies and T applies and L applies and those commands. Okay. So would you like to take that?
So just a clarification, right? So if given a data set and I tell the dependent variable what class I'm interested in, and
No, you normally generate, exactly, you can generate rule for a given class,
yeah.
or you generate it for every class. You run this iteratively until the entire data is consumed.
And we also need to mention the minimum confidence.
Minimum support and confidence. Or you may say amongst the things you pick the best one. Okay, but you can do minimum support, but don't worry about that. So normally what people do is they generate all the rules and then remove all the unnecessary, the ones that don't meet the criteria. That's a different problem. All I am looking at from your assignment is, if I give you a data set, you come back with a bunch of rules generated in a propositional sense.
To the order of identification.
You don't even know, that's the second assignment. Let's keep this independent. You randomly select a Y and then you use prism rule, then select another Y. You can see why this is called separate and conquer. The moment I generate a rule, I remove that data, I separate it out. And now I have a smaller set of data. Then I run. Then I separate. So finally I get a bunch of rules. Now a couple of things, when you are building this, remember always to use an estimate. Do you remember that? If I don't find a data point, the support is not 0. It is 0 plus 1 by n plus 1. Use that M estimate, otherwise your metric can go terribly wrong. Right? Second thing, is it a greedy approach or global search? Greedy. Clearly greedy, right? At any point I am just looking at what is the best at that point.
We are doing it exhaustively. We are doing it exhaustively.
No, we are not. So if I was doing exhaustively, I wouldn't have believed that this or this are the best. Maybe taking a second best here would have given me a better
We
thing.
are going to take that in the follow-up.
No, I don't, right? I only pick one of these two and add a new condition. I'm filtering by this only.
Then you are not going to go again.
That's it, it's over because the data is taken out. Some data I'm removing, right? In separate and conquer, once I finalize a rule, I take it out. So that data can never be tested on any other rule again. So this is a classically greedy analysis.
But even if we take the last 20-year production rate, then in the next step we are going to take age as the metric.
Exactly, but only on this data. Not on the remaining, I already filtered on this data, right? I already filtered on these 12 records. I will only work on these 12 records now. So at any point, I am taking the best possible step there and filtering. And now my next step is only on that filtered data. And I subfilter, finally I remove that data. Now I have the entire data, but I start with a different starting point. Right? Is the
I'm not understanding clearly. So you are saying that could have been a rule which could have been better than what we are creating.
So all I'm saying is, if I had, even in this case, let's say, if I had spectacle prescription is my own, I would have probably had a 12-member rule of which 3 are there, right? The next step would have been another one with 3 on 3, right? I will never know that because when I do the next iteration, I am not going to have these 4 records in it. They are removed. That's over. So I will not be able to test it out. So it's a clearly a greedy search.
So instead of a greedy search, if we went ahead and calculated it for myopia in this case,
Then it becomes an exhaustive search which is unmanageable.
after that we would look at a length, right? For
So, exactly. So one thing that people try, then I should not pick only the second way I should pick. If I just go unlimited, all 12 of them I should pick. But what people do is at any given point of time, they pick the top 3. This is called beam search. So it's not one thing that a best guy, I'll take first, second and third. Now, in the next level, I'll get 3 first, second and third for the first guy, first, second and third for the second guy, first, second and third for the third guy. So I have 9. Again, pick the best 3 from there. At any given point of time, you pick the top 3 instead of the topper. So you are slightly broadening your search from being absolutely greedy. You are allowing the second and third guys to contribute. You understood? First, you pick the top 3. By second level, I have 9. Pick the top 3. By third level, I have 9. Pick the top 3. By fourth level, I have 9. Pick the top 3 and just keep picking. Build up to 6 or 7 level rules.
6 length rules.
6 length rules. Sorry, 6 length rules. So ideally what I want in your homework is a assignment is a beam searched prism rule generator. You have that, you do it, write it well enough, you can make it a R library and just publish it. Seriously, I mean they don't have it, it will be a good service. I have built it, but as I said, the guys who bought the IP for what I just mentioned wanted it as part of that. So I couldn't publish it as a free R library. So the academician in me still feels a bit guilty. So I want to clear it off with you guys. So write it and just publish it as an open source library. For those of you who are planning to apply to US, this is a sure shot recipe to get an admission. You know, and not many students after masters will be able to do that.
By the way, once we do this 3D search also, are you assuring that you are covering 100% of the data?
You go up to 100%. So finally what you may do is you may generate a rule with only 1 record. So you separate, rest of the data you build a rule, separate. In the worst case, in the end you have 1 data left. That's a rule by itself. It didn't meet any of the previous conditions obviously, and hence it's a rule by itself. So you at this point do not decide which rules you drop out. The problem with Prism rule is you will create a million rules. But then you have the other batch is doing something else, right? So they will help you filter out the top 100 rules. So you don't set up a filter while generating the rule that I will not accept it. You generate all possible rules, as many as possible, and then pick the ones that are important. Even in decision tree, that's what you do. But this is a very different technique from decision tree. This is called separate and conquer rule induction. Decision tree, on the other hand, is divide and conquer rule induction. So it's a very different technique. When we get there, decision tree, I want to spend more time. That's more popular than this. This works pretty fast. This is great. I was told somewhere that Facebook uses it in its production environment. So it's a pretty powerful rule-inducing system, despite the simplicity of the algorithm. Algorithm is almost trivial, right? You know. So, the problem is it creates just way too many rules. So prioritizing becomes extremely difficult. So they have rules that they generated is if tier production is reduced, then length is none. Then tier production is normal and astigmatism is no, then contact lens is soft. Like that, they have created some 4 or 5 rules that cover the entire data. How many are rules? Problem is you end up generating too many rules. Right? So that brings us to both the assignments that I want you to do. In the lab sessions, Jagan will help you run the decision tree. So I don't want to give you an assignment on decision tree. It's too trivial. There are very matured algorithms. So you just run it in 2 hours, you will have the data, the results taken care. Whereas in these two, there's no maturity. So work on describing a rule. And ideally, if you want to thrill me, then write a mechanism in which you plug in an API into CART and C50 algorithms that you will study. They output the rule in a particular way. So your thing should read those rules and describe them the way you want to describe. Or at least couple with these Prism rule guys, you should read the rules that they generated and describe it in the way that your team designed. Whatever, support, confidence, lift, Q score, Z score. I mean, the naivest thing to do is actually report them all as in a table. Support is this much, confidence is this much, lift is this much, Q score is this much, Z score is this much.
So
you can do that, but do better than that.
decision tree, when it tries to split, right, it tries to make those two things very, very different when it makes that split.
We'll talk about that. It deserves a complete mention, so we'll study that. All I want you to know at this point is it's not separate and conquer. It's not taking one class, building a rule, then taking same class probably, building a different rule. It doesn't work like that. It works in a different mechanism. So that makes it my product. If I had 2 algorithms, Prism and decision tree, I would have created more rules than just decision tree and non-overlapping. Right? Because these are greedy, the set of rules that you generate need not be exhaustive, exclusive. So I'll generate multiple overlapping rules. Even in decision tree, there are multiple techniques, each one generates its own rules. Right? But we'll get there. Any questions on Prism? How energetic are you? Can you stretch for some more time? Yes? Oh. Yeah. Otherwise, today I'm a bit worried about giving a break. You are in a holiday mood, right? You are taking way too long to come back. If you take a oath that you will come back in 10 minutes, we'll take a break. 11? 10 minutes? 10:40 now, 10:50, sure. Okay. Okay. When you come back, we'll learn another technique of rule generation. That's quite a bit of time. So we can relax a bit. By the way, you don't have class on next Wednesday, it's regular next Friday. So that way you are fine. April 1st. Next class is on April 1st, yeah. So someone was, in my institute, there was a discussion. The Women's Day was on March 18th. So why don't they have Men's Day? They said that's what is April 1st, They just call it Fool's Day. One girl wrote, but men didn't agree, of course.
Hey, Wednesday.
So essentially, advantage of prepositional rule induction produces compact, understandable knowledge. We do have simple prepositional rules. Can find, the problem is, it can overfit. I can actually say, first I have identified 5 records, 10 records, like that I am removing. Finally, I may have rules that support only 1 or 2 records. So it will overfit. I generate all of them, then I remove a few of them as an important. And they can be slow to induce. Unlike decision trees, they are slow to induce. That's why these are not as common. But otherwise, they're pretty powerful. Pretty powerful. So beam search, now you know what to do. Yeah. So the second type of rule that we are going to generate are actually, interestingly, done in an unsupervised context. So far there is a while. There is a while. What if there is no while? While we didn't talk about recommendations, did we? Did we talk about recommendations? Recommendations is a very popular topic in data science. How do you recommend something to someone? How should Flipkart recommend a book to you?
Using SVD.
VD, what is it? SVD, using SVD. Absolutely. But is that the way? That's actually a very advanced way. Think about it. Philosophically, how do I make recommendations? There are 3 approaches I can do. Okay? SVD does something called collaborative filtering, which is a very interesting approach, a more advanced approach, where what I am saying is, I will recommend a book to you if he read a book, rated it high, and he is very similar to you. So I will recommend something to you if your similar people like you liked that book. Is that a good philosophy to recommend? It's a wonderful philosophy. Actually, it's a very nice way of doing. Think about it. The greatest way to make a recommendation is, I sit and say, what do you like? You like these 25 qualities. And now I measure in each book those 25 qualities and identify the book with highest possible mapping between your preference. You like 70% action, 10% drama, 5% comedy, whatever is your preference. Now I go and look for the books that have 70% action, 10% drama, 5% comedy, length of the book is 100 to 120 pages, color illustrations, whatever your preferences are, I identify for each one, I identify for each book, map them, give you, that's the most perfect way of recommending. Right? Matrix factorization essentially tries to accomplish that. But it's a very complicated thing. The second in the lever is, hey, I will identify a guy very similar to you. I will see what he liked. Whatever he liked, if you didn't read, I'll recommend it. This is what singular value decomposition accomplishes. I have all users, I know the distances between them. It's called collaborative filtering. Starting 2006, 2007, it became extremely popular. Great. But before that, the idea was even very simple. Idea was, in my purchase data, I will take intersections of all those, right? So I will arrange user 1, user 2, user 3, user 4, product 1, product 2, product 3, product 4, whether they bought or they didn't buy. That's that. And I will take intersections of all possible users. If there are the end users, I can do NC2 intersections. Okay. Now I will identify the ones that are most common. I will do NC3 intersections. I will do NC4 intersections. And I will identify those products that occurred in most intersections. So what I know is people who are buying this also are buying this in general. If you are Flipkart, even today, many of the companies just use something as simple as this. They just take intersections. If I have end users, from them identify This simple thing, people who buy this are mostly buying this product, then that becomes a recommendation. People who viewed this also view this. People who did this also did this. This is called association. Or I am looking for are associations. This is unsupervised. Is there a target here? No. My data system is U1, U2, U3 and P1, P2, P3, and I am saying people who buy P1 also buy P3. For the second, people who buy P2 also buy P7, P5, P6 by P9, like that. I'm just building. So this is an unsupervised rule generation engine, almost exhaustive search. In fact, it is exhaustive and hence extremely time consuming.
So in this kind of application 100% support is actually a good tool. Whoever is buying a mobile is also buying a mobile cover.
100% support is always a good rule. Only problem is it may be too trivial. So in this also, if I come back and say people who buy coffee are also buying milk.
But then maybe it's trivial, but we should not discard it because we buy coffee, we should recommend milk also.
So that's a question, right? That's always $1 million question. It's not that you are discarding it, it's prioritizing. So association rules gives 1,000 or 2,000. See, one of the problems with, one problem, why humans fail in stock market? Behaviorally, we are very short-sighted. We develop a bias very quickly. So you have developed association rules, some 10,000 association rules, and you put high support things up front. You gave it to your client. So he says, hey, first rule, people who buy coffee also buy media. What did you do? People who buy shoes also bought shoelaces. What are you doing, man? People who buy. Third thing is, by the third thing, they come to a conclusion. Whether then they go to their manager and say they generate all trivial rules like this. I have studied the rules and did that. So it's extremely important to prioritize things that are important to them. So only in that context I am saying, be careful when you are referring a 100%. Particularly if it is short. But the quality of the rule from a statistics perspective, of course I support this rule. Only from I understand triviality I am worried about I support this.
So,
You got a question.
yeah, so in the beginning of the lecture today, you mentioned that through this process we can only do the correlation, not causation.
Yes.
But I think we can also do causation. Right? For
You can.
example, you gave this example like people who bought shoes bought shoelaces, and the vice versa. People who bought shoelaces bought shoes. If I were to evaluate the proportion of people who bought shoelaces within the sample of those who bought shoes, if that is higher as compared to the denominator being shoelaces and the numerator being
Yeah,
shoes,
PA given B,
then I
B
know the
given A.
correlation is actually shoes
So is it,
shoelaces but not the vice versa.
It's always a problem, right? The causation, correlation. So the fundamental question, okay, people who buy book A bought book B. Right? Flipkart said. People who bought B bought book A. Now, can I ever say that buying B is caused by buying A or vice versa?
I evaluate the proportion of B given A and A
Yeah,
given
let's say whatever, B given A is, so people who bought Harry Potter 4 also bought Ramayana, let's say, with 90%. People who bought Ramayana also bought Harry Potter with 74%. By the way, here I am only measuring joint probabilities in this case, but I will use your PRISM or previous rules, I come up with different confidences. But in association rule, I am only doing joint probability. A rule. Now, PA given B, P given B given A. The first question that people ask is, you are only restricting your analysis to the X1, X2, X3, Y that you have in your data. Maybe the real factors are something that you didn't even consider. That people bought Ramayana and people bought Harry Potter is because people liked something else that may not even be part of the data. So then how we can assign
There
a...
could be so many latent factors. I'm
Exactly.
about it. Even A and B, which causes what?
More correlation is all you can say. You cannot say more correlation is causation.
I'm not saying correlation. I'm
No,
saying-
P of A given B, P of B given A, one is more than the other.
Yeah. So
Whatever.
That is
That
actually-
doesn't make it causation. That makes it better correlation than the reverse. Why does that? The causation is something, the factor, latent factor, there could be, all that has to be considered, right?
Within these two. which
Within
one
these
is-
two, that's not causation. Causation means everything. Within these two, I believe this caused this.
Which
more.
occurred first? I'm interested, right?
But that's not causation. Like true deaf people who argue against causation are not really worried about in these two. This is more correlated to this than this is. This is impacting this more than this. Yeah, fine. That could be the case.
No, can I, if I give you two numbers, P of A given B is 10% and B given A is 90%, right? Given these two numbers, can I say that A always occurs first as compared to B?
Yeah, it's like.
No, all you can say is B of A is a rule with higher confidence than A of B.
Sir, it could be like somebody.
It
who
doesn't
got
mean
the-
B causes A or A causes B. All it means is B given A is a rule with higher confidence than P A given B. Causation is a much more tricky business. Well, you can't, when you say, when you start claiming,
Infer, right? You can infer a little bit here, right?
you can, but when you claim causation, people read a lot more to it. People will say, have you considered all latent factors? Causation is causation. Newton's law says, gravity causes this thing. No question, you get into any level of latent factor, gravity causes it, that's it. There's a fundamental law, G m1 m2 by r squared. That is causation. Nothing else is allowed, no leeway. If I say Earth attracts moon, given I find a bigger planet, I find smaller planets around it, is a higher probability than given I find a smaller planet, bigger planets around it. Those are high confidence rules, correlations. But causation, no, there is something fundamental called gravity and curvature of space. I will never know that from these rules, but unless I explain that, I am not explaining causation. People are very stringent.
I think I'm not going beyond the.
That's not allowed.
No. If
No,
I were to
you-
evaluate two statements, because somebody bought shoes.
I understand what you are saying is, I have evaluated these two statements, and in these two statements, this statement has a higher conditional probability than this statement. You leave it at that, that's all you say. You cannot say, and hence this causes this, more than this causes this. That doesn't make any sense. Either it causes it or it doesn't cause it. This causes it more than it causes this is not allowed in that discussion. They don't give that leeway because they are vehemently fighting against you. So they say no, our directive learning tells in a completely different way, right? So it's the stringency of the requirement that is put by the causation guys that doesn't allow us to state what you are saying. So leave it at that. You just say P of A given B is better than P of B given A, and hence the confidence of this rule is more than that rule, and leave it at that. Yeah, you were saying something. You said.
So I was saying it could be the events like somebody who bought a gun also bought bullets. So then using some business sense we can still establish the rule.
Using some business sense. That's the whole point. Yes, you have to use some business sense. Mathematically, what the rules say is correlation. Some correlations are causations.
Yeah, but then-
Yeah, you have to use something else, which math doesn't teach.
so all the
And what happens is when you are building an expert system, you end up coding all statistically good rules, which some of them may be pure correlations. And hence, they claim is expert system truly an expert system because you use something else also, right? I mean, it's this debate between machine learners and rest of the philosophers. So it never ends. I mean, we'll end up spending a lot of time on that, but it is best to accept that what we do is correlation. Some of them, if we are lucky, will turn into causations.
the latent factors are best explained under the umbrella of business intuition.
Exactly. That's one. Business intuition and hence is needed. Yes, it is best left at that. Right? Okay. Now, coming to association rules, I'll do a little bit of math, very little, so that you get the intuition. There is a property called closure property. Closure property is if you have a set of elements and you have an operation. If that operation produces a member of that set only, so I take any set of a subset of numbers from that set, run an operation, the output should be a member of that set only, then that set is called closed under that operation. So natural numbers addition is a closed operation. I take any number of natural numbers from that set, add them, the output is another number of that set only. Convex data, essentially closed. On the other hand, natural numbers are not closed under subtraction or division. They are closed under addition and multiplication, but they are not closed under subtraction and division. Right? So that's the simple property that we will use for generating these rules. And so they are closed under these two. I should have said not closed under these two, subtraction and division. Jagan, please correct this. They are not closed under subtraction. So, downward closed is if a set is closed under a property and if all its subsets also obey the same property. So if all the subsets are closed under a property, if the superset also is closed under that property is called downward closed property. Okay. So, or the other way, if for this set to be closed, all the subsets must obey it. Must be closed under that. Then only this superset will be closed. Okay. Such a property is called downward closed. So I look at a set. You ask me, is it closed under this property? I may not know. All I will then do is I will check whether all its subsets, possible subsets, if I find one subset which is not closed under it, then I say this subset is not closed. Sorry, this set is not closed. That's the check I do, right? That's a very, very relevant check as we're going to look at. Now that you know what this is, what am I trying to do in generating rules? I am identifying frequent items. Frequent items. Frequent items are whether a particular intersection, whether these two items occur enough number of times. Right? That's what I want to do. Frequent items are downward closed, which means, and obviously intuitively you can think of it. If I claim that a 4-member system is frequent, product A, product B, product C, product D are frequent, I am saying. All I am saying is, if I say that any combination of these subsets, like I can write 4C1, 4C2, 4C3, all of them must be frequent. Does that make sense or not? What I am saying is, if I call a 4-member system as frequent, I want to find, using some property, identify those items that occur 20% or more times in my data. Then, if someone buys one, I will recommend the other. That's what I'll say. If an item occurred more than 20% of, if a combination occurred more than 80% of the times, more than 80% of the times, I will say people who buy this also buy this. Now, if I have given you 4 items and say all 4 occurred 80% or more times, all I am definitely saying that individually each one occurred 80% of the times or more. Any 2 combination occurred 80% or more. Any 3 combination occurred 80% or more. If and only if that is true, all 4 can occur 80% or more. Obviously, you can 4 occur 80% of the times if one of them occurred only 60%. There is no way it can do that. So frequent items is a downward closed property. If a n-member set is frequent, all n-1, n-2, n-3 up to 1 better be frequent. We'll use that property for deriving these rules. Are you with me? That's exactly what I'm trying to say. So if I claimed ABD is frequent, I am essentially saying AB is frequent, AD is frequent, BD is frequent. And I am saying A is frequent, B is frequent, D is frequent, and C is frequent. C need not be frequent. I only called about ABD, right? In that system, well, I need to remove that, but in that system it's not frequent. A, B, and D are frequent. Right? Now, let's look at a priori algorithm. There is a database of 5 items. Order 1, part 1, 3, 4. This is Flipkart. Obviously, Flipkart deals with million items. But intuitively, what they do? 5 items. 4 orders, 100, 200, 300, 400 are the order IDs. Don't worry about them. In this order, I bought 1, 3, 4. In this order, I bought 2, 3, 5. In this order, I bought 1, 2, 3, 5. In this order, 2, 5. My goal is to identify those associations whose support is at least 50%. Which means if A then B must, AB must occur, the A and B must occur 50% of the time, not if A and then B. I am saying probability of A and B. Whenever I find A, I also find B with a probability of 50%. Right? Vice versa, BA. So how do I do that? First I write individual one-member item sets. 1, 2, 3, 4, 5. And I count how many times 2 occurred, how many times 1 occurred twice, 2 occurred thrice, 3 occurred thrice, 4 occurred once, 5 occurred 3 times. So immediately, so totally there are 4 orders, right? So 50% is 2 orders. Anything that is less than 2 doesn't qualify. So I can immediately drop 4. Because 4 occurred only 1 time. Anything that combines with 4 cannot occur more than 50%. Because 4 itself is 25%. So I dropped 4. Now I write all possible combinations that I can form with 1, 2, 3, 5. 1, 2, 1, 3, 1, 5, 2, 3, 2, 5, 3, 5. This is a all 2-member sets that are possible. Now you can imagine Flipkart's plight. They have probably 350,000 items, Amazon and Flipkart. So for them doing association analysis is a pain. There are some nice computational structures that people develop, but still it's a fairly tough problem. Okay. Now in this 1, 2 occurred once, 1, 3 occurred twice, 2, 3 occurred twice, 2, 5. So I drop 1, 2 and 1, 5. 1, 2 and 1, 5 I drop. I get now 1, 3, 2, 3, 2, 5, 3, 5. 2, 2, 3, 2. All these are minimums. So far I haven't used any downward closure property. Now I will use it. Now, let's say one thing I want to form is 1, 2, 3. One possible, now I have to form a 3-member set, right? 1, 2, 3. Can I form 1, 2, 3? 1, 3, 2, 3, 1, 2 is not there. If 1, 2, 3 is frequent item, its downward close means 1, 2, 1, 3, 2, 3 should all be the frequent. But 1, 2 is not there, so I cannot form. I will not even form 1, 2, 3. That's the advantage here. Is everyone with me? Yeah. So 2, 3, 5 on the other hand, I have 2, 3, I have 2, 5, I have 3, 5. So the only 3-member set I can form is 2, 3, 5. I cannot do anything else. I can't do 1, 3, 5 because I don't have 1, 5. 1, 2, 3, I cannot do any other possibility. So that's it. Now from 3 to 4, if there was a possibility, here there is only 1, but if there are multiple 3 to 4s, I check whether all 3s are there, all 2s are there, and I will ignore anything that is not downward closed. 2, 3, 5. That's it. That's it. Now I have a bunch of 1-level rules, 2-level rules, 3-level rules. But 1 level is not very interesting. Now I can write if 1 then 2. No, I can't write because there is no. If 1 then 3, if 2 then 3, if 2 then 5, if 3 then 5, if 2 3 then 5, if 3 5 then 2, if 2 5 then 3. I can write all of them as this. That's it. This is pretty simple. But this is an exhaustive search.
With the big data.
With the big data, it is, I have to do several data scans, right? So that is a problem. So people have invented something called FP trees. I'll explain it now, and I'll share a few slides. Jagan, just remind me. Do you have FP tree?
I have it.
You can share. So essentially, what people do is you created. The problem with this is I have to do several data scans. Right? Yeah. It takes a lot of time. So people use a data structure where I will start with, I will reorganize these things. Which item occurred most number of times? 5, 2 and 3 occurred more number of times, right? So what I will do is, I will construct a stop right. I'll construct a tree where I put 5 in the top, then 3, then 2. I'll go highest, second highest, I'll organize them in this order. Then what happens is the one that is highest, it will form a branch like this. All rules. So one time I construct this tree structure, I'll be able to read my rules and do my confidences from that tree. So what people have invented is something called FP tree structure, where you organize the most frequent items at the top and least frequent items at the bottom in a tree structure, and then you will read out the rules from it. I'll share a few slides with you. It's fairly straightforward. If needed, I will talk about it in the next class. Right? So the fundamental difference between association rule and prism rule is association rule is unsupervised. I do not need a target item. You can build an association rule even with supervised learning, where if you specify y is equal to s, I will first subset the data with y is equal to s. And then I'll keep all the possible combinations. I do my association rules only in that subset, and then attach y in the end. So I can do that. Is that clear? So technically, if you want me to run it in a supervised context, I can subset the data. Now I have 3 subsets. Any association rule that I generate 2, 3, 5, then I can write it as a rule as if 2, 3, 5, then 5. If 3, 8, 9, then y is equal to no. Like that I can actually tag it at the end. So you can do association rule in a supervised setting, but the beauty of association rule is it's unsupervised.
Creating the after the association, 2, 3, 5 already told us that we can forward downward.
Exactly. 2, 3, 5 have a 50% support.
Okay, but with that 2, 3, 5 can occur with a yes, can occur with a no. So defining the rules is separate.
Whichever is the, so if you have really 2 rules, where if 2, 3, 5 then S is a 71% support, 2, 3, 5 then no is a say 69 support, you either decide. You can manually say, if they are defining 2 complementary classes, you pick the higher support, provided the lower support is less than certain value, or the difference is less than.
What helps the association rule give us the creating that?
Because it said 2, 3, 5. So otherwise it would have, it still has given me the subset of rules that have enough frequency in that particular class. Attributes that occurred. Essentially in Prism rule, I am building step by step. Here also I am building step by step within each subset.
But
This is exhaustive.
normally we are creating rules which have very high support.
Very high support. Exactly. You said that support.
So as such, it's not serving any other purpose but for the support. Right?
No, it doesn't. It doesn't. So that's why many people don't like it. IBM has invented it in 1990s. So what should I do? Given an order data, I should actually convert it into a thing like this where I have U1, U2, U3, user 1, user 2, user 3, product 1, product 2, product 3, like that. Normally in order table, people have a different way to store. They will have order ID. They will have order ID and product ID. So they say order 1, product 1, order 1, product 2, order 1, product 3, 3 items are bought. Order 2, product 7, like that they do. Order 3, like that they do. Order 3, product 8, 9, like that. This has to be transposed first into order IDs, order 1, 2, 3, 4 and product ID 1, 2, 3, 4, and then put whether in that order that item is there or not, and then do this intersection analysis as I mentioned. So there is a pre-processing from this data to actually, what is it called? Melt, cast, decast, right? Cast or recasting. You have to first cast the data. The Jagan will introduce you to A rules library, which has built in all these commands. Okay, so you can there is a nice algorithm in R to do visualize and do the rules. I think it's called A rules and A rules Viz. Okay. Any questions on A rules? Except it was a popular technique in recommendations until this collaborative filtering came. What do you think is the advantage of this compared to collaborative filtering? Advantage is disadvantage. Think about it. Why do you think A rules is good or bad? It's time consuming and all that. Business wise. Good, exhaustive search and hence it's time consuming. But there is a fundamental advantage here. Easy is never a reason anymore. Like present rule is also easy. Business wise, is there a, do I need to know the user ID for this? No. This is a lot more suitable for Reliance than for Flipkart. In Reliance, no, they don't know who you are. Collaborative filtering, how does it work? I will identify the guys who are closest to you, and then whether he liked it, then I recommend. In Reliance, unless you are on a loyalty card, which is like probably 5% of their customers, 99% of the people are walk-ins. Does your grocery store know who you are when you are buying, and you may do a cash transaction? All they have is in one cart what items are there. In that order ID, what items are there is the only information they have. Unlike your online store where they ask you to do the credit card, so they generate a user ID for you. Hopefully you use the same credit card several times, or you have some login password that you give where they'll be able to tag. But many physical stores where they don't have a mechanism to tag a user, all they have is order information. Then why do you use all these things for your discount, for your loyalty planning? On Christmas Day, you want to say multiple items that are basketed together. Gift basket you want to create. You don't have any information about individual user, this technique still works. That to me is the biggest advantage of association rules. Even today, when I don't have a way to identify a user in any way, and still want to design a loyalty gift basket or some kind of a deal, if people who buy this also get a 20% discount on this. If I don't have to customize, do a rule, then associations work. None of the other things, the more advanced techniques require identification of the user, which is anyway de facto in e-commerce. So when IBM invented this, they invented it for Walmarts of the world, where they didn't know who was buying.
What one actually tracks?
Now, this is in 1990. So when the technology was even, internet was not there, nothing is there, let's say. Now, obviously, with collaborative filtering, you have a more refined system. So, one way, you can think of this as a technique of the past. But I still, when I don't know, Flipkart, when it still says people who buy this also buy that, think about it. Even in an e-commerce scenario, if I go to Flipkart, they don't know who I am at this point, probably. I just click on something, they say you should probably see all this. When I buy it, they know who I am. But if I logged out, they don't know, right? But they're still recommending. The moment I go to a page, they say these are the other 5 books, Amazon. They must be using this.
When you're a guest, use them when you log. When you're a guest.
Yeah, when I just www.amazon.com, still they start showing things, right? They must be using this only. There's no way for them to know who I am. They use cookies. Maybe they use.
Yeah, they know which device.
If they know that it's me, and if I bought before, they can do collaborative.
One thing which I'm not sure and maybe they should do is like selective pricing.
Exactly. The moment they do selective, then some of them are trying to do, but for that they need to know who you are with cookies or something. Then they can do.
Yeah, if the customer really wants it, they can increase the price.
Exactly, they can increase the price. They can and even customization. Once I was, this one around 10 years back. In Air, I am a Singapore citizen. I love Singapore Airlines. Man, they are good. They are good. Trust me. Once one of the clients invited me to US, and I was traveling in business class. I got in Chennai. This is like 6-7 years back. Chennai to Singapore. That lady came and she asked, "Do you want any magazine?" I said, "I want India Today." She said, "Oh, I said, there are lots of non-Indian magazines, so I wanted an Indian magazine." So I said, "I want India Today." She went, she searched, and she came. Now, 4 hours, and then the next Singapore flight from Singapore to Los Angeles. She said that the air hostess came and said, that India Today you must have read, or do you want me to give it to you? This is a different flight. But the information has gone in already that I prefer India Today. So this lady came and she said, that you must have read, or do you want me to give it to you? She had that with her. Scary, it's not yet. Now, after 15 days, when I took the return flight from San Francisco to Singapore, that lady gave me the next edition of India Today. She said, "This is your preference." That was custom. But same ticket, right? She knew it was me. The moment they know it, they personalize and customize. In hotels nowadays, once Hilton or someone asked me to come up with personal preferences. So when you check into a hotel, what kind of food you order, what kind of things. So the very expensive hotels now want to have. I believe once I was in Seattle, I was told that Bill Gates' house, and maybe I'm sure Mukesh Ambani's house has it, has a internal personalization technique. So it actually allows you to change the color of the walls and the music you hear. So walls don't have a color, like they don't paint it, they have lights inside. So you prefer some shade of orange and yellow with that music, and then automatically it personalizes for you. When you go to the next room, that room looks like how you want it. So people in these very high-end places are looking at using these for unbelievable levels of customization. It is scary. Okay, yeah, exactly. Exactly. See, there are some of those things are just descriptive stats on you. They just followed you very closely. Some of them are actually association rules, where you do, this buying this and this also leads to this.
Gathering information about how much time I will take based on traffic association. Because it would have you have calculated the time that the cars took from point A to point B during that.
This one it actually does, traffic indicator. Google, I predict, does Google forecast or does it just show at that time what is the traffic at that time? At that time, then it's collecting the data most likely.
Travel, how much time will it take in night will be different from how much time will it take?
But will it tell you now how much time it will take tomorrow?
Yeah.
Okay, then it's forecasting.
The way we do it is different.
No, it will be different. When you are traveling, if it tells you, it's not doing analytics. If I can ask now how much time it takes, and if it tells me accurately, maybe it is just taking an average. I don't know. Okay. Right. Okay. Last half hour. Okay. We'll not take a break. Should we or no? We will not come back if I give you a break now. So let's stretch for another 30 minutes. Today you have an exam? No. Good. Yeah. One more reason to celebrate. Right. So we'll get to the most popular of the list, which is the decision trees. Okay. So obviously the top 1 and 10. The top 10 algorithms, first one and 10th one are decision trees. So this is a very, very important, powerful technique. Better, more respected than both Prism rules and association rules. Okay. Association rule, in the lab you just practice how to run A rules and A rules visualization, nothing more than that. Right. Now, just read out a rule from this. Tell me one rule. We have done this before, so tell me slightly. Actually, we can start from there. Even let's not even.
Height of people.
Let's not even.
Height of people take.
I'm not even asking you to build a rule for me. I'm asking you randomly pick an attribute. Okay? Then we will generate rules. So one attribute that I picked is CC average. Let's say I randomly picked an attribute. We'll obviously not randomly pick an attribute. But for the time being, let's assume we randomly picked an attribute. To see how important it is to not randomly pick an attribute. Let's say I got lucky and I picked CC average. Previously, there are 13, the data has 13 records, 6 of them were no, and 7 of them were yes. See, this is a very, very complex data. It's almost like coin toss. 50% or no, 50% or yes. Almost, right? And I picked CC average. Now, there are 3 classes in CC average. Low, medium, high. There are 8 low, 3 medium, and 2 high. 8 low, of them 6 are no, this is not low, this is no, and 2 are yes. This is the low bucket, CC average, low bucket. CC average, medium bucket, all 3 are yes. CC average, high bucket, all 2 are yes. This is wonderful. What was what I did, if I think of it graphically, is my data was a collection of yeses and nos. Right? I figured out that if I divide the data by 3 classes, in some classes I have all positives, in some classes I have mostly negatives. What was almost an equal distribution with just one split based on CC average became a very homogeneous setup. This is wonderful. This is wonderful, right? From almost 50% mess, almost 50%. Now this is 100% yes buckets, medium and high. This is almost 75% no bucket. Great. I may decide to stop here, or I may add one more randomly I pick and add one more attribute. So this is divide and conquer. I take an attribute and simultaneously I am dividing it into 3 buckets. or n number of buckets if there are n levels. Now I add one more attribute here. If it is not complete, I can add one more attribute here. I create, at any given point, I am dividing the data. Previously, I am building a rule and separating that data, building the rule on the rest of the data, building the rule on the rest of the data. Here I am not doing that. I am taking one attribute, I am dividing based on its levels. So I am creating 3 separate filters. CC average is low is one Excel, CC average is medium is one Excel, CC average is high is another Excel. Now in this Excel I can add, if it's homogeneous, great. If it's not, I will divide this into 3 other Excels. This into 2 other Excels. On independent criteria, I can do. And so finally I will have 1000 different Excels if I have 1000 rules. Right? We haven't figured out how to do it yet, but conceptually it's very different from this. Let's say I randomly pick the family size. Instead of this, I pick this randomly. Now this has 4 classes, 1, 2, 3, 4. Family size 1, family size 2, family size 3, family size 4. In family size 1, I have 4 records, 2 of them are no, 2 of them are yes. In family size 2, only 1 record. 3, I have 2 records, 1 no, 1 yes. 4, I have 6 records, 3 no, 3 yes. Has it gotten any better? If anything, it got slightly worse. Before that, I have a slightly higher probability for yes. Here, absolutely equal probabilities in 3 of those cases, right? Now, let's say I divide this with age. Again, I take the second attribute randomly. No records here, no records here. Again, 4 records, 2 yes. So, one thing that we definitely, certainly now know is we shouldn't randomly pick the attributes. Because the right attribute selection can lead to shorter, simpler rules. Occam's razor. You want as short a rule as possible, right? So, one of the tasks that we need to solve in a decision tree is which attribute to pick. Okay. We'll get there, but let's get the nomenclature right. People call these where I am picking an attribute. So here I picked an attribute. In this case, I picked an attribute here and I picked an attribute here. Places where I pick an attribute, they are called the nodes. They are the decision points. And the topmost thing is called root node. So you can think of this as root is up and all the tree is inverted. There is a root up and then there is a tree. I mean, I don't know, I never understood why this looks like a tree, but they call it a tree. These finally decision-making points are called leaves. Okay, bottom leaves. And the connections are called branches. If family is 4 and age is medium and something else is something, that is called a branch. So that's the nomenclature people use, nodes, leaves and branch. And those trees with just one node is called a stump, decision stump. Okay? But decision tree is where you start with a node, you call that root node, divide the data, and then identify another node, and then identify another node. You keep adding nodes for all of them until you get to a set of branches where each branch is homogeneous. A branch is if this and this and this and this. You can read a decision tree as a rule, right? This one is if family is 1 and age is medium and something is something, then they will not buy. If like that, each branch is a rule, right? It's a very important skill. In fact, one of the homeworks that Jagan will do is he will give you a decision tree. You have to read out the rules from there. It's very simple. You guys should do it. Normally, when I'm doing a management level course, that's the whole focus. Given a decision tree, how do you read the rules? But I will not even focus on that for you. You should be able to read it without any problem. Right. So the only challenge, there are only 2 challenges now. Where to start and where to end. I have to pick the right guy and I have to know where I should stop. Let's think about, before we get there, let's understand geometrically, statistically decision trees. Each tree is a root. If a CC average is medium, each branch that leads to the same class can be combined with R's. So if this is a branch that said yes, this is another branch that said yes, what I'm saying is if x1 and x2 and x3 are, if y1 and y2 and y3, then yes, class is yes. So all branches are connected by R's. Within a branch, all things are connected with an end. This is called disjunctive normal form. By the way, did you guys study logic, computational logic in your undergrad? You must have done truth tables and all that stuff, right? There's a lot of theoretical studies here. This is called disjunctive normal form. If A and B are C and D are E and F, then K is in disjunctive normal form, and you can prove that when things are in disjunctive normal form, you can convert them into simple end rules. Let's not worry about this. In fact, if someone says this, just don't get scared, because they're talking about addition. Graphically, what's a decision tree? We have already seen it several times. Decision tree is a systematic axis parallel split of the space. Axis parallel. We will learn axis non-parallel oblique trees, but at this point when I say if x1 is A, x2 is B, x3 is C, I am drawing axis parallel splits. In high dimensions, I am drawing axis parallel hypercuboids. Decision tree is a axis parallel split of the space. You can look at it like that. So there are two independently extremely intuitive ways of looking at. I think for engineers, this is a more exciting intuition. For business guys, this is a more exciting intuition. Decision tree is a collection of roots. Is for business users. Decision tree is axis parallel hypercuboids, and we are weird. We find that easy, right? But this is a very, very interesting thing. Now, statisticians, on the other hand, think completely differently. Decision trees as viewed by statisticians is really crazy. They look at it like your linear regression. What was in your linear regression, what was the thing? Oh, sorry, I didn't mean anything against statisticians, but it just is that, I mean, engineers are in the middle of weirdness, statisticians, so we are slightly bad. If you think about linear regression, what did we learn? There is a hypothesis that y is equal to m1 x1 plus m2 x2 plus c. What is the best m1 m2 that leads to the least error? Statisticians essentially think that there is a possible infinite number of decision trees that can be built. So decision tree is my hypothesis. So I can split the space into infinite number of rectangles. That rectangular distribution, which minimizes the error, is the best tree.
So is it infinite number of rectangles or
Infinite combination of rectangles, like your y is equal to m1 x2 x1, m1 m2 can take infinite values. So what I was saying, I can draw infinite lines. Like that, I can split the space like this, or I could have split it like this, and I could have split it in some other way. There are all possibilities. Now, my machine learning is using gradient descent, a greedy approach, figure out the best way to split. That's what we learned in linear regression, right? There are infinite possibilities for M1, M2, M3. Using gradient descent or some greedy method, I found the best values of M1, M2. So statisticians think about a decision tree as there are infinite ways in which you could have split the space. Using a greedy approach, find the one of the local optima of splitting the space. Local, we will see very clearly that it's a greedy approach. So that is the statistician's way of thinking what is the best tree here? When I do this, I need to define exactly my linear regression. What is the best M1 and 2?
Highest accuracy.
Highest accuracy, if I didn't regularize. Highest accuracy with the lowest value of theta 1 square plus theta 2 square, whatever, if I regularized. Right? Same here. Highest accuracy, but smallest possibility. Number of nodes, here you can think of equivalent of your theta 1, theta 2, theta 3, here is the number of nodes I used. So the tree with smallest error, with smallest number of nodes is my Occam's razor. So that's what I minimize. I build a tree with the smallest error with smallest nodes. We haven't figured out how to do that, but ideally that's what I want. How we do that is what we study. But before we get there, I really want to revel in the beauty of decision trees. They are fast. I mean, if I figure out where to start, it's like, identify the attributes, split it, it is beautiful. I don't need to tell it anything. It just does it. It's robust. What do I mean by robust? Robust means if I do it, you do it, he does it, we get the same result. If I have given you a data set and ask you to build a decision tree, if I give to all 40 of you and that's all the information I give, build a decision tree, you all come back with the same result. Whereas if I ask you to build a neural net, you come with 40 different answers. Because you will have, logistic regression is robust. Logistic regression is fast. Requires very little expectation. And nicely you might build some intuitions about customer base that the business itself doesn't know. See, it's actually amazing that I could go back and tell a doctor that if the father's blood group is B positive, mother smoked during her pregnancy and kid eats more than 70% carbohydrate, he will have asthma. That guy didn't know that. And if you ask me what is asthma, I don't know. That's the level of medical knowledge I have. So once I was working for Ohio State's political advising group. So that guy who I was working with was a political advisor to the Ohio governor for the past 15 years, an MA in political science from Yale University, and 15 years of political advisory for the governor of Ohio. So he asked us, I went back to him and I said, if in a county you have white majority and more jute mills, okay, focus on public transport. He was shocked. He said, how did you know this? What do you know about American election system? He said. I said, only thing I know is it's crazy. I don't know what county is, but I know that, before the actual election happens, you guys fight so much that you are tired. I mean, Trump and the other guy, and Hillary and the other guy are fighting tooth and nail now. They are not even the actual contestants. The actual contestant will be one guy from here and one guy from there, right? By then, they are exhausted. I don't understand that. I mean, why are you tiring your guys so much, But anyway, that has its own merits. Anyway, that's okay. But the point is, I said I don't know anything about it. I don't know what a county is. And do you know what a county in US is? I knew what state is, but I didn't know what a county is. Then he said, how did you actually do this? I said, I just followed 3 things. I looked at all the county data that you had given. And first I identified those counties where the results are changing between elections. They gave me multiple past election data. Some counties are bastions for Republicans, some counties were forks for Democrats. They don't change. Past 30 years, the same guy is winning, same party is winning. So no point even in trying anything there. Done. But there are enough counties where the results are fluctuating. There is a distribution. 40% of the times Republicans won, 60% of the times Democrats won, vice versa, like that. So I picked first those counties. And then I looked at my target attribute as a problem, major problem that they highlighted, which was part of the data. And I identified sub-segments. And where there was a white minority and number of jute mills are high, the biggest complaint people were talking about was commute to the office workplace. I got that decision rule. When I ran a decision tree, I got if whites are a minority and dominant industry is jute, then biggest complaint is commute to the workplace. And that had enough support and confidence. So I told him, because if that is the biggest worry, talk about public transport. That's how I did. Now this, you can see how amazing it is. Talking to a political advisor to a governor, a Yale political science major with 15 years of experience in Ohio, didn't know this. And I ran it in probably, he gave me the data, some 500, 600,000 voters in various counties in Ohio. At county level he had given. Various properties, some 500 properties, 50 counties, 100 elections. That is the data. And once the data is there, organize it in a format and then run a decision tree. You will see it's probably 15 minutes.
When you said that decision trees are robust, just not discussing when you start with different attributes, the decision tree
Will be different.
will be different. You are saying there is always a metric which can
Exactly.
govern which metric to start.
Exactly. Which attribute to start. That's what we are going to learn. Yes. There are multiple techniques to pick that attribute, but once you choose so why do I have C4.5 and CART? They're two different, if you remember when at the beginning of the class I showed top 10 algorithms, top one is C4.5, 10th one is CART, right? They use two different metrics to decide which attribute it is. But yes, they are different attributes. So you guys also will go soon. Don't envy him so much.
About decision trees, I need to have all the variables as categorical variables.
Excellent question, I'll answer it next week. No, the answer is no, you don't have to. But naturally, a decision tree looks like it's all, even a fundamental question, should a target attribute be categorical or numeric? Can it only do regression or classification, or can it also do regression? It can do both, we'll look at it, but not now.
It's both supervised and non-supervised.
It is supervised, always. No,
When
wait.
we generate tools,
My why is there, right? Unless I have whether they take a loan or not. All these things.
You're taking the why including in the rules, right?
Say that
There is
again?
going to be a part of it.
Yeah, this is my right hand side, that is fixed.
That's my target function.
Target, so it is supervised. The question is, under supervised, is it regression or classification? Should it be numeric or categorical? I cannot build a decision tree if it's not supervised. Like prism rule, I cannot. If nothing, then something I have to specify, then only I can build this side of the rule. So they are supervised.
Basically, the supervision part comes at the lowest level, where the segregated to yes or yes.
Yes or no.
At all other levels, it's just a category.
Categories are, they can be numeric also, we'll talk about that. But decision tree needs to have a target attribute, and the target can be numeric or categorical. At this point, we'll talk about these things in great detail, but don't worry, by the time next class is done, you will become masters of decision tree. Everything there is to learn about decision trees, you will have learned. We'll go in that pace, we'll slowly do it, because it's one of the most exciting and important techniques. Okay. Okay, that's the next question anyway that I asked. Right, I think it's a good time to stop today. So when we meet in the next class, what we will start with is how do we build a decision tree? How do we pick an attribute and how do we grow it? There is some math, but where the intuition is decision tree is essentially constructing a tree. If I know how to pick an attribute, then at least I can grow indefinite overfitting trees. I have to stop it at the right point. That's another challenge. Otherwise, I can keep drawing a smaller and smaller and smaller rectangle and get to some highly overfit conditions. But we'll learn. Good. Any questions? If none, yeah. Just